Right, everyone. So welcome to this Co-UDlabs webinar on techniques for monitoring the underground infrastructure. So just some housekeeping, I guess, first. So for all attendees, we would please ask you to, we'll see at the end of every talk. So we'll put up the agenda. You have seen the agenda. Hopefully we'll put it up in a few moments as well. So if there's a little bit of time at the end of every speaker, you can ask some questions straight away. If there's not enough time, then we please ask you to just keep asking the questions later, and just use the chat also for asking questions, so we can all practice the chat. And of course we have the discussion right at the end as well, if there's not really much space for questions. So I'm just going to say hi to everyone in the chat. So you can chat to everyone and say, hello, everyone, and people can just test their chat. So if you look at the bottom of the screen, you can see the chat function. So that's good. I can see some attendees also saying hello and good morning. So if you look at the chat, so there's like at the bottom row, there's a little chat bubble. You can just say, hi, everyone.
Good morning.
So yeah, we please ask people to use the chat to ask questions when we don't have time anymore at the end of the slides. And then I can see we have 23 attendees, and I can see lots of hello, everyone. So it looks like a lot of people have worked out how the chat works, which is good news. I guess most of us are still used to online meetings now. So you see the agenda for this morning. We have myself and Ian Naismith hosting the webinar, and we'll have a range of exciting speakers who will all introduce. And then I guess first of all, we'll let Ian Naismith introducing the rest of the Co-UDlabs project itself.
Thanks very much. As you will be aware, the reason that we're gathering today is because we are reaching the end of the Co-UDlabs, the Consortium of Urban Drainage Laboratories project. And this project has been running for the last 4 years, funded by the European Commission's Horizon 2020 initiative. And this is due to end in the next few months. In fact, in March, we have a final meeting in Brussels where we are presenting what we've done and what next. But essentially what this has involved is a consortium of 7 research facilities spread around Europe and supported by 2 organizations in France, Unovia and Grai, who assist with the communications and the dissemination elements of the project. Now, over those 4 years, we've been able to cover a rather large range of projects, all about improving the way in which urban drainage research is undertaken and to encourage collaboration. With Horizon 2020, this particular project was about starting a community of research infrastructures that perhaps had not actually worked together before, and to get people across Europe thinking about how to work together, because urban drainage is an issue which affects everybody, and we're all subject to the same issues of climate change. So Co-UDlabs has 3 goals. First of all was fostering cooperation through networking activities. The second element of it, which a number of you have been involved in probably, has been the transnational access. And I'd just like to label the point there. What the EU was funding was researchers, municipalities from one country using a facility in a different country. So, for example, Germans could not use the IKT facility, the British could not use the Sheffield facility. You had to go to another country. And it forces us to everybody to realize that perhaps we should always be looking for the best facility for our research, and we should be collaborating. And the third element was actual research activities. So the consortium partners have been undertaking a range of research activity with each other, involving experimentation, involving literature reviews, things like working out how best to share data, how to collect data, how to store data, looking to see what the differences are between countries in the way in which we perhaps describe data. So this has been extremely helpful for everybody involved in taking this forward and setting the base for it. And in a moment, I'll explain or Alma will explain where do we go to next after this. So with the one item I would mention is that there is one further webinar workshop to come on the 11th of March. And with that, we're going to be looking at all three of the joint research activities that were undertaken and what has been learned from those. So looking at the transnational access, I'll just give you a few statistics because this explains what has been one of the great results of the Consortium of Urban Drainage Labs. And that is that we've actually conducted 31 projects spread across the different facilities there are 17 different research facilities across the the seven partners. And as a result of that, we've had 3 different calls for transnational access projects, 227 user group members from 26 countries have participated. 11 of them were non-EU. And we even had a number of non-EU group leaders running some of these projects. And you can get an indication over on the little diagram here. We've had North America, we've had South America, we've had Europe, we've had a number of Asian countries as well represented, including China, in some of the projects that have been undertaken within Co-UDlabs. And going forward, this is one of the areas where people will find this of use. Everything gets published on the Co-UDlabs website. And you don't need to see the detail of this. This is the different facilities and their names, but essentially between us, we were able to cover surface runoff pollution with test facilities for that, the performance of assets, sustainable urban drainage systems, and in-sewer processes. Together, what one needs to realize as well, often when people talk about urban drainage, you're thinking about sustainable drainage, SUDs, surface runoff, but we're also talking about wastewater. And of course, in many cases, these are mixed together in combined sewers. And so it's been a very broad spread of activities, and all of those transnational access projects I was mentioning have been undertaken. And we're going to hear about 1 or 2 of those transnational access projects today, which we're using to illustrate some of what we've found with regards to the monitoring of underground infrastructures. So as regards these joint research activities, the first one was smart sensoring and monitoring, essentially looking for new technologies, sensors, materials, methods, protocols, and analysis. And it's all about being able to have evidence-based decision-making. The second one of the joint research activities is evaluating assets, how they deteriorate. And experimentation was undertaken on a number of aspects of deterioration, including looking at what are typical damage scenarios that you find with underground infrastructure. And finally, the third activity is improving resilience, how to make more efficient, sustainable, and good performing urban drainage. And we're looking here across the board. Often there's a lot of focus on climate change, but it's pollution. pollution, flooding, and vulnerability. They all mix together. And so we are going to cover these off. I will make a brief mention here of this one upcoming event, which is a further online workshop on the 11th of March in the morning, where the leader of each one of our joint research activities will explain the key lessons that were learnt. There'll be a couple of short illustrations and an explanation. So if you've been interested in what we've heard today, you'll be able to hear from the leader of the joint research activity on monitoring on the 11th, if you'd like to join us again. And then a question of what happens next with the Consortium of Urban Drainage Labs. This consortium has run for 4 years. It is ending in 2025, but it is a startup community. So the intention is that further research funding will be sought and obtained to take this particular group forward. But in the meantime, I will hand over to Alma to explain UDrain working group, which is intended to take what we've done much wider in the meantime.
Yes, thank you, Ian. Yeah, so the UDrain working group, for people maybe not aware of how they're all lots of different. So there's a lot of different active urban drainage working group. So one of these is the IWA and the IAHR. So that's a big, the International Water Association, the International Association of Hydraulic Research. They have a number of combined committees. So one of them is the Joint Committee of Urban Drainage. And under the Joint Committee of Urban Drainage, there are a lot of active working groups. Some of you may be familiar with them. Some of them may be not familiar with these. Some of them have been active for many years. And also we have just started, following from the Co-UDlabs, a new working group called the UDrain Working Group. So this is just free for anyone to join. So for the moment, this will be, if you're interested in joining us, please contact the Co-UDlabs. So I'll put the email that's on the slide. Ooh, there's the web page. Yeah, so I shall put it in the message, sorry. There we go. Anyway, I'll type it in. I don't know why. At Co-UDlabs.eu. So at the moment, this is being hosted. So the Joint Committee Urban Drainage has just a lot of websites, and we're just redone the website. So you can look also here. You can see where in future it will be hosted. And this is just free for everyone to join. So please send an email to like Co-UDlabs saying, oh, I want to join this. And then for any future, or if you're interested in how this works with all the working group, you can go on the Joint Committee Urban Drainage website. But the main thing of this is to establish like an ongoing working group around the first worldwide network of large research infrastructures of urban drainage systems. So we're working on preparing an inventory and an atlas of large-scale research infrastructures on urban drainage. So the idea is to not replicate. This is the whole idea that was behind setting up the Co-UDlabs project as well. We don't want to replicate in many different countries these really rather large research infrastructure, but we want to share data and have people travel to this, because not everyone, it wouldn't be very efficient for everyone to build up their own. If you look at IKT, they have really enormous testing setup for testing buried infrastructure. We have some other very specialist one in Sheffield and in A Coruña, but also others. So this is also open to anybody not from original Co-UDlabs Co-UDlabs project. So the idea is to just build a community of these large research infrastructure owners to also like enhance access to lots of different infrastructures for everyone, but also to work on uniform practices. So actually we also realized as part of the Co-UDlabs research, there's not really as yet a very clear international ontology on urban drainage, on definitions of different parameters, which kind of, if you think of all the future data-driven AI type research, is kind of hampering progress, because what somebody might call a water depth or a water level, or there's not. So the idea is really to also work towards more uniform practices and having a more uniform language, so that data can be more easily shared and more easily understood as well. So the idea of this working group is to organize a congress, webinars, and other training events, so that even the Co-UDlabs project itself finishes in April, but there will be, through this UDrain, which is hosted under the JCUD website, and therefore will just keep hopefully going on for many, many years, not just for the individual project. And you can see there in future coming posted our upcoming webinars, and we meet during the Joint Committee Urban Drainage, sort of they host a range of conferences. So for example, the Urban Drainage Modeling Conference in Innsbruck this year, and the year after it will be the Sewer Processing Networks in Trondheim, and last year there was the ICUD in Delft. So there's a host of conferences around urban drainage organized, and within these conferences you also get meetings of the working groups and workshops, and this is free for everyone to join. So you don't have to be, so everyone that's interested is, you don't have to have a big research infrastructure yourself. You can just be interested in learning what are there. You don't have to be a professor, or you don't have to be an academic. You can be from anywhere, from practitioner, PhD student, master student. Everyone is free to join these working groups. So that was it. I think over to
Thank you.
Ian.
Well, the great news is that we are slightly ahead of time. So I will stop sharing, and Joshua, hand over to you to take over sharing your slides and doing the first presentation, and over to you, Alma, to introduce that.
Yeah, and I guess in the meantime, I'm just checking for any attendees questions so far. No, not yet. Just making sure we start in good time.
Joshua, we can see your slides now. So if you would like to start your, oh no, hang on. Now you can see me. Now we can see your main slide. Okay.
Yeah, just need to make sure I was unmuted before starting, otherwise it'd been a very boring 20 minutes.
Right, and I will mute myself, and over to you to introduce yourself and your topic.
Hi, yes, so I'm Dr. Joshua Myrons. I work at South West Water, and I work closely with a team of us in the organisation, and alongside two partner organisations, so the University of Exeter, also based in the Southwest, and recently very happy to announce that we've formed a collaboration or partnership with iTouch Systems, who provide lots of software and hardware for surveying urban drainage systems out in the UK, and I think slightly further afield now as well, which is really great. And so today I'm going to be talking about a project that's kind of defined my career so far, which is the automated inspection of CCTV sewers using computer vision. So a little bit of a background before I get any further. This project started as my PhD project back in 2015. So that lasted 3.5 years. I learned a lot about urban drainage systems. I was a computer scientist by trade, so I learned a lot about urban drainage systems. And then Southwest Water picked this project up from 2018 to see about the feasibility of such a study. And as of 2021, I was granted a Future Leaders Fellowship, which is a prestigious fellowship in the UK, to carry on this research. And we've got, similarly to the Co-UDlabs, it's ending this year, so hopefully there's lots of interesting things that we can share with the community. So what is the project itself? So the aim of the project back when I started was to identify faults and features in pipes using only raw CCTV footage. As you probably all already know, CCTV footage is used, especially in the UK, for all sewer inspections. So it's a real important part of all maintenance or rehabilitation. So whenever anything happens in the pipe, whether that's we're called out to a blockage or we're doing major civil works, CCTV surveys are done before and after every time we touch those pipes. So first off to check what's going on, and then afterwards to check that we haven't broken anything else and everything is fixed as it should be. As part of these surveys, all the faults and features in that pipe should be annotated. In South West Water, we do this to the WRC specifications. So there's a manual of sewer condition classification that's used pretty much universally across the UK, and variants of it I know are used across the world. And that, I believe, off the top of my head, contains around 250, 260 fault codes for annotating what's going on in the pipe at any one point. That is quite a complex set of codes, and due to the kind of skills required for this, that annotation process and working out what's going on in those pipes can be a really time-consuming and expensive process. So in some systems or in some organizations, you will record all the footage in that pipe and then you will take it offline afterwards, and a technician in office will go through, rewatch that footage and label up what's going on. But what's more common practice nowadays is for the camera to be pushed through the pipes and the surveyor annotate that on site, which is slightly more efficient. But that leads on to my next point, that human coding is somewhat unreliable. So I hope not to put too many noses out of joint, but it's a really challenging task, especially if you're doing this live on site. So there's a story I always tell with this presentation and the project in general. But you can take a well-trained surveyor and you can put them in, I guess, the middle of a field on a sunny Tuesday afternoon, no distractions around. They've got all the time in the world to do the survey, and it will go really well. They'll probably produce lots of really good annotations. They'll have the time and space to annotate all of those smaller faults that you might not normally annotate, and you get a really good quality survey. Unfortunately, that is the ideal world, and what the real world tends to be is you take exactly the same surveyor on a really wet, miserable Friday evening. They're having to do traffic management in the middle of the road while putting the camera through the pipe and annotating software, and unfortunately, the quality of annotation tends to drop. So I don't write it in the presentation, but one piece of work that we have done is we set out to set a gold standard of CCTV surveys. So we took 20 videos, we gave all 20 videos to 3 different surveyors and asked them to label up what's going on in those videos. And some of them were quite complex and quite long. There was videos that were maybe an hour long of pipes. And the idea being, if we get all of those labels from those 3 different surveyors, we can combine them together and we'll have the perfect benchmark set so that we can test our AI against what we know is the right answer. Unfortunately, when those came back, there was lots of disagreement between all 3 surveyors. So this was in an ideal environment, and there's a lot of subjectivity depending on experience and training and things like that. But what we found, I think, in some of those videos, the best kind of level of inter-annotator agreement was about 50%. So we knew that there was a challenge in the industry there. So going through all that background, as I've already mentioned, the aim of this project is to use AI to improve the quality and efficiency of sewer surveying. We only want to use raw CCTV footage for the time being. I know there are lots of really, really interesting technologies that we'll hopefully hear about over the rest of the morning that we could combine and do lots of really, really cool things and improve results with. At the moment, we're only focusing on the UK standards, but the hope is that they transfer lots of different standards across the world. And we also want to develop methods that are capable of working in real time and on site. There's lots of really powerful machine learning and deep learning algorithms out there, but a lot of them require a really powerful GPU or real kind of heavy software infrastructure to work in a good time. We want to get something that's really lightweight, and so you can get it on site and someone can get insights straight away. So those are the 3 kind of main goals that we've got for the project. So the technology itself, I've spent quite a long time with my team developing this. So as I've already mentioned, it's based on the WRC's manual of sewer condition classification. And this is based on research from the University South West Water. At the moment, this is only built on a library of 90,000 labeled images. So I won't go too much into the machine learning and data science behind this, but that's, in the grand scheme of things, a very small set of labeled images, and they haven't all been verified. So these are taken directly from what surveyors have historically provided for South West Water in the past. Fortunately, as part of this partnership that we've set up with iTouch Systems, they are generating probably that many images a week, if not more. And we're hoping to get access to, I think the last count, which I think was about a year ago, was about 4.5 million images. I know that's increasing exponentially. So hopefully that will help our algorithms going forwards. What the functionality includes for those algorithms, there's lots that's going on. So initial fault detection, is there a fault in this image or not? And then classification, what types of fault are in that image, alongside, as you can see in kind of the examples we've got here, object detection and localization, so we can see where in the image those faults happen to be. And there's lots of other bits that we can do, and I'll talk about those later as well. I've already mentioned that the aim is to implement this on-site as close to site as possible, and you can see in the bottom right, the picture here is us with the technology running in a demo environment on one of the little iTouch red boxes. So this is what a surveyor would take out to site. You can just about see at the bottom there, there's a camera reel. So that'll be a semi kind of rigid cable that you'll force through the pipe. There's a camera on the end of it, and that'll collect the footage. And this is probably as powerful as a small laptop computer on top. So it'll display what's going on, and you can ask the AI to do things alongside that, which is really great. I've mentioned the data, so this kind of highlights another challenge with this. We've already used historic surveys from multiple sources, so there's a lot of subjectivity that I've already mentioned. And the other thing I kind of want to highlight now is the huge disparity in fault representation. So as you can see from this lovely pie chart, this is a kind of representation of the distribution of faults within South West Water within our data set. There's lots of cracks and fractures. They make up a significant chunk of those. They're really common. Root intrusions are pretty common, and deposits are pretty common. Fortunately, things like collapses, I don't even think that makes it on there, and obstacles make up a tiny fraction of the data set, which from South West Water's asset management point of view is great. That means we don't have many of those faults because those are critical to the infrastructure and usually result in imminent failure. But from a data science point of view, when you've got, I don't know, 20,000 images of fractures and only, 30 images of collapses, the machine learning models don't perform quite well at that. So there's been quite a lot of effort across the industry in the UK to build a data set that's a bit more representative, and so we can get some more examples of those faults. And that is the WRC data set that I'm going to mention here. So this was a joint project. I think there were 7 water companies involved in this, and everyone came together and provided some data to the WRC, so the kind of standards, the people that are setting the standards for sewer surveying. And yes, the WRC went away and validated all of this data for us. So we knew that we were getting good examples of everything. And I think their aim was to get about 1,000 examples of each fault. We fell a little bit short of that, especially in some of those more obscure faults. I think spiral fractures and cracks, I think between all of the water companies that participated in the end, we maybe had less than 50 examples, which shows that some of these things are quite challenging to find in the field. But what's really important about that project was an Ofwat project, and that data is now publicly available. So I think there's about 27,000 images in there that anybody can access to have a go at this. And I think there's lots of really interesting things going on there. As I've already mentioned, iTouch dataset is providing 4.5 million images. And again, that gold standard surveys, I've already mentioned the challenges we had with that one. So hopefully this runs relatively smoothly, but these are some demo videos that have been taken straight from, I think, a conference that our supply chain partner hosted last year. And as long as the fidelity of the video footage is good, you should be able to see that lots of faults are being identified here. So in this image alone, there's quite a lot going on that's working in real time. So you can see there's a red border around the image. So we had a fault detector working to identify whether there was a fault or not. We had the object detection. So that's where the little boxes are flashing up saying what's going on. Those are all assigned to a single fault code most of the time. So that's a joint displaced up there. We'll see the confidence score of that fault next to it. And we'll also see, there's another video that I can go on to here for serviceability ones. A clock reference, these are really important additions to the code that need to be identified. And as I mentioned, there's lots of other cool things we can do. So we can automatically read out the chainage, so the distance down the pipe at the bottom, the pipe material, and we're also looking at things like identifying the water level, the depth of field and things like that, which are really useful for accurately identifying exactly where in a pipe faults are. I'll just leave this one to finish. I think this might be the last example. So there's other tools and techniques. So I alluded to at the start that we're using a combination of deep learning and traditional tools, or traditional computer vision techniques. So we're starting off with a really traditional, real lightweight technique. So for chainage reading, we're using, I think, a random forest classifier, and we provide it the segmentation mask around where that chainage would be, and we achieve a 99% accuracy. Unfortunately, there's lots of different text, fonts and shapes and colors and sizes, and we do have to train on the relevant footage to achieve that level of accuracy. But once we know we can do that, that's really good. I know there'll be questions like, well, you can in theory take this directly from the reel that's kind of recorded and put into the video footage straight up. That's great, and if we can do that, we will do that. But a lot of the time, water companies are interested in look at their historic footage, so that information still needs to be read from the frame. Another one that I mentioned was clock reference. So fortunately, because we're able to put a bounding box around where the fault is, we can look at the relative position of that bounding box to the center of the pipe. So first we have to identify the center of the pipe, look at where that bounding box is, and we can assign clock references to it. Just to note why that's important. So say, for example, fractures in different positions in the pipe imply different things. So if you've got fractures running along the side of the pipe, that implies compression, and so on and so forth. Another one, percentage cover. So you can see in these really cool images here that once we've identified that fault, we can segment it. So in this case, a vermin code, so a rat, has been identified, and using a segmentation algorithm, we can identify exactly where that is within that image. Not so useful for a rat. That's just more for our own fun. But say with root intrusions or displaced joints, now you have a percentage of that surface of that cross-sectional area of that pipe that will cover, and so you can use a trained regressor model to identify exactly what percentage that covers. Again, this is really important for the faults, for identifying the difference between different faults. So say a root intrusion that was a mass intrusion that covered 10% of the pipe. Yes, we need to clean that, but it won't affect serviceability too much over the next couple of weeks. If that mass root intrusion actually covered 90% of the pipe, we need to do something about that now, because that's going to block imminently. And if it blocks, there's a chance of a flooding or a pollution event, which is really costly to the organization. The only one that I haven't got here that I have alluded to as well is we're looking at depth estimation as well. So it's really exciting that you are able to identify the depth within an image with some really clever deep learning. I know there are lots of other technologies that will do this better. For example, ultrasound or lasers could do this better. But again, when you're looking at historic video footage, we don't necessarily have that information. So able to provide any depth in the field information is really useful for identifying exactly where faults are. So coming on to the kind of tail end of the presentation now. So the project itself, I've mentioned this is a three-party collaboration. So Southwest Water is the host of this project. We kind of will be hopefully the end users of this technology, and the primary beneficiary of the research we're doing here. iTouch Systems, who are the supply chain partner, and are implementing it. So at the moment, our entire fleet of, I think it's 60 odd vans all have an iTouch system. And so we're going to embed it in our first kind of instance so that we can get this to people in the field as quickly as possible. They're also, as I've mentioned, providing all of the 4.5 million images for verifying our algorithms and improving them. And then the University of Exeter, who's been involved from the start, is our technical knowledge base, providing lots of guidance support on AI. The project itself, so the R&D part is part funded by UKRI. So as I alluded to at the start, I'm a Future Leaders Fellowship. I'm a Future Leaders Fellow. So half of the money from the research comes from them. And I have a team, including me, of 4 developers working on this. So that's not just the implementation, I say software developers, but that's also the research as well. So with a lot of these AI algorithms, as you can kind of see in the literature and the media, every month there's almost a new computer vision algorithm that's being released. And so we need to keep on top of that and identify what works best for us in this application. The timeline for this project at the moment, so as I said, it comes to an end in October this year. So we've got a collaboration agreement in place now to start getting this technology out. We've applied for further funding, so hopefully that will go through. But at the moment, the key kind of piece of work is testing all of our algorithms on iTouch's data. So in theory, by summer this year, we'll have the algorithm and methods out on site with our surveyors, and getting some real results, rather than just demos in closed rooms, so we can show off what's going on. And finally, the benefits of this project. So obviously there's a commercial product, which is why iTouch wants to be involved and all of that good stuff. But from a South West Water perspective, we're hoping to see improved survey efficiency and accuracy. So the accuracy I've already alluded to, and even if there is a comparable level of accuracy, at least that accuracy will be uniform. So the algorithm should be relatively deterministic in its approach. So even if it's shown 2 videos of fractures, it will identify them both as fractures, whereas 2 separate surveyors might identify one as a fracture and one as a crack, and it's quite hard to compare at that point. We're hoping that this should reduce survey time on site by around 10%, just reducing the amount of cognitive load on the surveyor for labelling. And in kind of real money terms, we estimate that to be an efficiency saving alone of around £200,000 per year, which is great. And that doesn't touch on all of the many regulatory penalties and fees that come alongside being a water company if things go wrong. So if we were able to, say, reduce blockages by 5% in a year, that might actually reduce the number of pollution events by, I don't know, 3 or 4 events per year. And I think off the top of my head, the regulatory penalties for pollution events for UK water companies, or at least South West Water this coming year, are around £200,000 per event. So even if we can reduce a couple of those, not only do we help the environment quite a lot, but we justify the research and hope that there's more that we can do to help that. It's a very evident benefit, but we will provide better network visibility. So we are able to perform more surveys if they're more efficient, resolve more network issues. Our ability to look at all of our historic data, so retroactively labeling previously unlabeled footage, allows us to reference that in the past. So we've got terabytes and terabytes of footage, but it's not been labeled. It's just been recorded for a very specific purpose. And it was a lot cheaper at the time not to get it labeled up. And so that's kind of not very useful to us now. If we are able to label that up, we can then start comparing between footage, so looking at degradation of faults over time. So actually find out that, say, a structural defect that we recorded, I don't know, 5 years ago in a pipe hasn't actually decayed over those last 5 years when we've done the next survey. Maybe we can triage our systems and spend that money elsewhere for the time being, because it's not causing any problems in the meantime. So that would be a really great benefit to our asset management team and those guys that are planning out our kind of big strategic works. Improved brand and reputation. South West Water isn't known for being the most innovative, but it's changing. We've won awards for this project, which is great, and I think it started out building those connections. So, for example, we wouldn't have been part of the WRC data gathering project if it wasn't for this research, and so we're kind of building that network and now starting to do a lot more innovative stuff ourselves, and further R&D options, which we'll hope to exploit future development opportunities going forward. So that was a whistle-stop tour of the project. If there's anyone who's really interested in the data science or stuff behind the scenes, I want to ask more about it, please do so. We can take this conversation offline if they're not relevant for everybody. But that's my presentation. So thank you very much, and I'll open up to questions.
Thank you.
Thank you, Josh. So there seems to be questions in the chat. So I can see the first question from Wim Bonte from AQF, which I think stands for Aquafin. So yeah, it's a question in two parts. So why making an AI-based automated annotation software when there's already software available? I agree it's a challenge and a sign of time, but maybe also a waste of time. So I suppose there's questions here from me to both. So maybe Josh, what makes your AI maybe different to others? And then I guess to Wim Bonte, maybe would you like to share a link to a publication of the other AI techniques you are hinting on in your question?
Yes. So if I get that right, so there are a couple of competitors out there in the field, and they've emerged over the last probably 3 or 4 years since COVID. And yes, this project started kind of well before that, more as a research project than a commercial project. What we're aiming to, and I guess the universal selling point of this project, is that we're trying to get everything on site. So a lot of those other technologies out there at the moment, as I alluded to, you need to use quite heavy computational resources. So you will record your survey, you will then send it off to a server, and depending on which one you're looking at, there'll be various timelines to get that back. What we're hoping to do as part of this project and the extension to this project is get this on site and giving real-time feedback to a surveyor. So as they're pushing the camera down a pipe, it will flash up and tell them that this is here, almost like a little kind of guide on their shoulder that's going along and being like, oh, you might have missed this. Can we label this up? Are you sure that that's a crack? Maybe it's a fracture. Or even if we're able to automatically populate those fields that they have to fill in as they're going down, that saves them a lot of time and effort. And as far as a couple of the other AI things, yes, I'm happy to. I'll pop my Google Scholar in chat so you can have a look through there, and there'll be lots of publications linked through that as well. So hopefully that answers more questions. But if there's more on that one, do let me know.
Yes, so I can see both Wim has also shared another, like palon.com, and also another question from John Rostrom. So here we build smartness on top of an old CCTV or video. Do we see video as the future censoring technique, or will other new techniques like acoustic radar or ultrasound take over and then apply AI smartness on top of such data instead?
Yes, that's a really good question, and hopefully that's something that will be discussed across this workshop as well, because I know there's some other censoring techniques. So yes, it's really good to make use of all that historic data, and the current industry standard is CCTV videos. I think there really is a lot of merit in combining those technologies for the time being. For example, acoustics or LiDAR or lasers, laser information combined with that CCTV, you're going to get a lot more information back, a lot more accuracy. And for some of those folks, you're going to get a lot more insights behind them, which is great. Unfortunately, at the moment, I don't think the industry is necessarily in a place to adopt some of those technologies quite as readily. They're quite, especially in the UK and Southwest, slow to adopt new technologies. So I think they'll have to supplement CCTV footage for the time being, just while confidence is built in the new technologies. Most of the works, before anything's even commissioned by an asset manager, they want to look at a picture of what's going on. So we're still going to need that camera there. So we should still do something with that information. But hopefully in, I don't know, a couple of years' time, when some of the other technologies have built confidence with different water companies, then we might be able to lean away from some CCTV footage to do much faster kind of surveys and then combine that information with CCTV footage when relevant. So that's my opinion on that one, and I'm sure there'll be lots of discussion about it later.
Right, so then we have another question incoming from Wim Bonte again. Will different types of camera systems and methods be challenged, like standard CCTV, robot crawler, 360-degree camera, stationary zoom inspections?
Yes, so that's another really interesting one. There is lots of video footage out there, and I've seen some really impressive results with the zoom cameras as well. I think a lot of the techniques we're applying will apply to those different types of survey inspection. I know you can do some more interesting things with those as well. So the 360-degree cameras are really interesting. You can kind of reconstruct scenes with those 360-degree cameras. So you use depth estimation to build a 3D model of that pipe as well. But yes, I think there are challenges. They aren't necessarily widespread at the moment, so they haven't been fully tested. But I have a feeling that a lot of the AI techniques we're looking at given the right time, will be applicable to those as well. So again, it'll be it's almost like another sensor system that we can augment and combine that information with.
Right, so I guess we have a few minutes in case there's any other questions for Joshua. Yeah, and I guess Joshua, if when the next speaker is, or while we change over, if you're, feel free to share your Google Scholar or any publications on this in the chat, because as Wim also said, it's supposed to be a collaboration group and webinar and knowledge exchange. And I think that the question really hints, so why do we need another AI when there's already AI? It really hints to the challenge, I guess, we have of changing all the latest knowledge and all the latest, there's so much being produced, how we keep on top of challenging or collaborating and exchanging knowledge with everyone. It's part of why we do the webinar, of course, but
yeah. And I would say on that one, like the fields of computer vision and computer science are just going so fast at the moment. It's really hard work to keep on top. So there hasn't been that many publications from the project since I moved to Southwest Water, and there's all sorts in the field now. Every probably 6 months there's a new breakthrough that makes the AI even better. So this is why it looks like we keep needing new AIs, if that makes sense, because there is a more efficient one, there is a more accurate one. So yeah, lots of really interesting things in that field at the moment.
Thank you. I was wondering, Manuel, do you want to start sharing so we can have your presentation up for the next session?
yeah, so the next, I guess, well, in any way, if anybody comes up with another question for Joshua, I guess it would also be really helpful as the webinar progresses to say, we have the discussion, of course, in the end, but in order for it not to become confusing, sort of introduce yourself and also say, this is a question still for Joshua. Because if you're anything like me, I usually come up with a question about 20 minutes after the event. So I'm sure that might be the same for some other people.
Yeah, definitely. I'll keep an eye on
We
the
will
chat.
keep a chat on the, we will keep an eye on the chat. And also, is this for everyone? Feel free to also share any comments or web link or publications. So we have, we're running well on time. So I guess our next speaker is Manu Reguero-Picayo, who was very active in Co-UDlabs. He did different transnational access. I see a nice picture here in Manu in Sheffield on the front. And he will talk about monitoring sediment dynamics in the underground hydraulic structures using thermal processes. And he did this as part of TNA visits. So he went to both the AWAG and he went to Deltares and he went to Sheffield. And also I'm conscious of the time because I guess we don't want Manu to start too early in case people come in.
Can you hear me well,
In and out.
Alma?
Yeah, can we hear you? Yes, we can hear you.
And you see the presentation, right? Not
And we
the
can see the presentation, yes.
Okay. Thank you for your introduction to the topic. So shall we wait or whatever you tell me?
Yeah, I'm just thinking if people dip in and out if we run too early.
Okay.
On the other hand, I could see 35 attendees, so I think most of the people that want to be here are here anyway. So I guess we may as well start and stay good time. It's 49 now anyway. Yeah, just start.
Okay. Okay, perfect. Thank you, Alma, again for the introduction. Hello, everybody. Good morning. I'm going to share what Alma said. A research. It was part of or most of my postdoctoral work during the last years. And it was really very related with the project Co-UDlabs as I was moving through different partners, not only transnational access, also part of these activities are involved with the joint research activities. Basically, I'm focusing in sediments, in trying to understand, and not only to understand, also to measure the accumulation in urban drainage systems. So basically, to put some context to this topic, the main causes of that produce these accumulations are insufficient flows in these systems and also the particle setting after the storm events. And the main consequences is that these systems get reduced and lost discharge capacity. these sediments may produce blockages, and in some cases even floods, combined sewer overflows, and then other stuff like gas productions, bad odors, and along, etc. So when we are talking about sediments or measuring sediments, we talk about sediment depth, to how to measure this variable. And if we have a look to the past and also current experiences, we observe that there are not so many field experiments, and those that already exist are very local campaigns. Then another issue is that a lot of the devices or the technologies that are currently available are really expensive and also requires a high maintenance. And this produces that to develop a system to monitor sediments in a urban scale is very difficult to scale. And also we have the opportunity, we saw a presentation just before, to use inspections to detect these sediments. However, we cannot use this kind of inspections to have an online monitoring in case we want to develop a strategy for maintenance and cleaning of these systems. With all this context, we proposed a system based on temperature sensors in order to estimate the sediment depths in this urban drainage system. So basically, we have, I'm going to put the pointer. Yeah, we have on the left temperature sensors, and the idea is to obtain, using these temperature measurements, obtain the sediment depth. So in the middle here, what we need is to understand the analysis of the heat transfer processes. So basically, this equation, that is the heat transfer equation, in order to move from the temperature measurements to this sediment depth. And basically, what my postdoctoral work was related was to understand this connection, this analysis of the heat transfer processes. And the applications that we look at during these years was on the one hand, sewer pipes, so the accumulation in sewer pipes. For that, we took some references of temperatures of the wastewater in sewers, and also gallipots, where it was the other system that we put the attention. And as well, we have a look on how the temperature dynamics look like. For that, we couldn't find so many references, but we installed some sensors to have an idea of how the temperatures change in these systems. So we talk about heat transfer processes. So the point is that at the beginning, we have some preliminary tests in the University of A Coruña. And for that, we took like just a couple of sensors. So one was at very bottom and one was in the water layer. We introducing some temperature changes in the water. We observed that when the temperature was changed in the water phase, there is like a diffusion of the heat through the sediment layer. So we could measure this, as we have also this second sensor. And if we have a look to the graphs, we observe this kind of attenuation and also time shift of the curve of the temperature. So by analyzing this, the previous equation, the heat transfer equation, we found that there is this kind of attenuation and shift differences. And simulating and modeling this equation, we have here these dashed lines. We can predict based on the water temperature and the sediment depth. We can model the temperature at the bottom of the sediment. But the idea for us is the opposite, like using the temperature both at the top and at the top, I mean in the water layer and in the bottom, try to get the sediment depth in this case. And for that, we develop a system that we call it MONSE, that is the acronym of Monitoring Temperatures in Sediments. It's an Arduino-based system that is composed with more than two. That was in the first preliminary test. So we installed more sensors, and also introduces an active heater also as well. Here was the first prototype for the lab, and this is one already used in the field for field measurements. Basically, the heater, just to explain why we use a heater, is we develop this with the heater, this dual-proof heat pulse that basically is used to define the thermal properties of the sediment. So with that, here in the differential equation, we have the thermal diffusivity. So we have a device that can measure the thermal properties of the sediment in order to then estimate with a better accuracy the sediment depth using this equation. The technology development, so all these processes was, as I already mentioned, was developed in the framework of the project Co-UDlabs. I mainly, in these partners, EAVAC, I started with EAVAC, then I moved to Deltares. I also spent some months in Lyon at INSA doing some accuracy uncertainty analysis. And then I also did a short stay in the University of Sheffield and everything. Well, I was involved in the University of A Coruña, so I'm postdoc in this university. So here in Coruña, we start the first experiments, then related with the sewer pipes application. I was at EAVAC doing some lab scale mobile, and also all the development of the electronics was done at EAVAC. And I performed a lab scale test also in an annular flume in the University of Sheffield. And regarding the gallipods, I went to Deltares. I used a gallipod scale, one-to-one scale model to perform some laboratory tests. And also then I moved to the field in the Netherlands and also in Switzerland for long-term monitoring. So in order to understand the thermal properties in these two applications, first I will start with the sewer pipes. The first thing that we need, it was the measurements, real measurements in the pipes, how this dynamics looks like in a real sewer. So we took data from the Urban Water Observatory at that belongs to the EAVAC, and we saw that the wastewater temperature shows like a similar pattern that the flow with during dry weather periods, like a sinusoidal wave. So this information, we use it, so the temperature in the wastewater, to design, for example, when I was in the University of Sheffield, experimental campaign in the lab in order to first define the conditions of the wastewater and trying with different sediment layers. And why we use this annular flume test? Because we could simulate the flow conditions with different flow velocities and, as I mentioned, different sediment layers. So basically, we installed different sensors in the cross sections, trying with different sediment depths. Again, we focus in the sensors in the water and at the bottom for this case study. As I mentioned, we could reproduce the wastewater temperature patterns in sewers in the lab, and we test different gradients or daily gradients. And this is the results with the temperatures in the bottom of the sediments for different sediment depths. So you see again that we have this wastewater in blue, and then how this sinusoidal curve is getting attenuated and time shifted as far with the increase of the sediment depth. But how we get the sediment depth from this information? So as this is a sinusoidal curve, we can do a frequency analysis and get the amplitudes and the phases, and operating and doing some amplitude ratios and time phase differences. We can get these harmonic features, and we could compare it with the sediment depth. So for that, we previously simulate a lot of scenarios with different characteristics of sediments as well. And so if we compare the amplitude ratios or the time phase differences, we can easily get the information of the sediment depth or sediment height. These are the results that we found in the for the experiments in the annular flume. So how we estimate this sediment depth based on the different conditions. Not only the different sediment depths, but also including the flow, different flow scenarios. So we want also to quantify how the flow rate influences these estimations. And we found as a first result that the larger the temperature fluctuations, so the temperature gradient, the better the precision, the better the accuracy. We also observed that the sediment depth estimation decreases as the flow velocity increases. However, the influence of the velocity was lower than 1 centimeter. So for us, it was good enough to say that the flow is not a main issue in order to simulate the complexity of these heat transfer processes. And with that, we could remove the flow measurement from this equation. And also, in general, we found a good agreement between the estimations and the reference sediment depths with accuracies of plus minus 7 millimeters. And regarding the other application, the gallipods, it was also quite new. In this case, we, as I mentioned before, we didn't have any reference measurements. So basically, we installed some sensors in the field in order to have some reference temperatures before moving to the lab to understand these heat transfer processes. And well, yeah, here you could see in the graph how in this case the rain influences the rain or the runoff getting into the gallipot, how influences the temperature of the water inside in the gallipot. And this is what we use for designing the experimental campaign, and also what we use to then get the information of the sediment accumulation. So in Deltares, they had a 1-to-1 scale gallipot, and basically it works like this. It's a closed loop, but the water enters from here, goes into the gallipot. Then here is like the mixing process of the water with some sediment accumulation with the sediment layer at the bottom, then the outflow, and also it has like a big tank. So this gallipot is placed in a big tank in order to set the boundary conditions, so try to reproduce the soil temperature dynamics surrounding the gallipot. We test different hydrographs, different temperature gradients. These are the negative ones, but we also test positive gradients. We test with different sediment samples, different sediment depths, and this is how it looks like, the result of a test. So again, in this case, this is a negative gradient, so a negative oscillation of the temperature of the water, and this is how the temperature is attenuated through the sediment layer. In this case, we have more sensors distributed vertically in the gallipot, and one is representing the temperature at the bottom. So it's very, very attenuated. At one, the temperature 10 centimeters below from the bottom. That is also quite attenuated. In order to get the information of the sediment depth, in this case, we use again the heat transfer equation with a top boundary condition of which is the water temperature, and wall and bottom boundary conditions in order to reproduce the heat conduction in the walls and in the bottom. And with that, comparing with the reference measurements, we also obtain a high accuracy of the estimations, and comparing with the reference measurements, we observe mean average errors less than 1 centimeter and maximums less than 3 centimeters. We test this as well in the field, not only in the Netherlands, as well in Switzerland, in collaboration in the Netherlands with local authorities and also companies, and in Switzerland with another university and the canton of Zurich. With that, we could also test different gallipot configurations. For example, in the Netherlands are quite, let's say, small in terms of volume, or much smaller than in Zurich. So we could also test the robustness of this Monse system in order to be applied in the field. Regarding the field measurements, this is how they look like. So for like almost 2 months of measurements of temperature, here we have in blue again the temperature in the water layer, then in dark brown or in brown the temperature at the bottom of the gallipot, and in orange the temperature at a distance of 10 centimeters from the bottom. So we can observe again this when for example, in this rain, well, we observe first a lot of negative gradients, but also some positive gradients, and they are related with the rainfall runoff processes. And yeah, having a look in one specific rainfall event, we observe the same as in the lab. So basically, when the peak of the runoff appears and gets into the gallipot, this cools down, in this case, the water temperature, and these sensors that are buried in the sediment layer gets the signal attenuated and also time shifted. With that, with every single well, it's not a rainfall event, but we can single like temperature change event, let's call it like this, we can obtain one of these dots points in the sediment buildup graph. So with that we can plot like how is increasing the accumulation in the gallipots, and we also compare it with some reference measurements with like a manual measurement with a stick. We could compare it, having a good results or a good comparison. And with that, I reached the conclusion slide. Just mention that this Monse system, based on temperature sensor, was provide a novel opportunity to monitor sediment depths by analyzing the heat transfer processes. These measurements are focused in the attenuation and time shift. This system also includes an active system, which is a dual proof heat pulse module, which provides also a measurement of the thermal properties. It's true that it could be simplified. So with the collecting more and more data, we can range the value of these thermal properties. So even we can, in the near future, use data sets of these values to avoid installing this active heat system. without losing a lot of accuracy in the sediment depth estimation. And yeah, basically this technology can be low cost because these temperature sensors are could be really cheap, and they are also with that easy to scale and implement in urban drainage systems in order to improve the inspection and cleaning strategies regarding with the sediment accumulation. Just this is my presentation. Thank you everyone for your attention, and I would like to thank not only the project Co-UDlabs itself, also the partners involved, especially those ones which I was doing my research. Thank you.
Right, thank you, Manu. So I'm looking at the chat. We already have a question here. We have a question from John Rostam. It says, here the IoT sensors are at the bottom and at the top of the manhole. What then about the operational aspect when these manholes or gully pots are being emptied? Do you have to remove the sensors before removing sand? Would it be better to have a sensor measuring from a distance? So the conclusion is the temperature approach scalable for wide use in water companies?
Yes, thank you for the question. It's very interesting. So because we have a lot of discussion when I was in the Netherlands in Deltares regarding this. And for example, currently we came up to a solution that we found that the better way to install it, at least in Zurich, with a big gallipots or gallipots with a big volume, is to install this system to be easy removable. So you basically have to unscrew this one and then took out like in a pole all the sensors with the box with all the electronics, and then you can perform the cleaning. Because for example, the solution that we test also in the Netherlands, and it worked also perhaps for this type of geometries and gallipots. It was attached and glued to the wall in the corners, in the edges of the gallipot, just to thinking in, for example, a vacuum system cleaning the gallipot to avoid destroying the or removing everything from the gallipot. But I think that the better solution is the second one, like the one in which you can remove it easily and then place it back again to inside the gallipot.
Okay, thank you. So are there any more questions for Manu? And I guess it's nice to see after having you in the lab in Sheffield, one and a half year ago, that also Rotterdam Council was interested. So of course they are a practitioner. So have you got any more news of how they might be implementing it or be interested to implement it there?
No, yeah, right now we don't. Well, it's not active the collaboration, but with Deltares and Antonio, probably in the coming months we will try to restart again this collaboration. But also another ones pop up in the meantime, like in other countries. So I think it's scalable in terms of or transfer to another countries, contexts. So even another types of now we are trying to apply this system to another urban drainage systems. So not only gallipots and sewer pipes, also other ones. So it's also a change of the typical way to understand and approach this sediment accumulation problem, which is for example, using like, I don't know, other type of sensors or introducing a lot of velocity meters or flow meters. In this case, it's just measuring temperatures. You can even detect. I mean, because here I'm in the presentation, I was very focused on the precision accuracy of the sediment depth estimations, but you can easily build a system with just observing the changes in the temperature to detect, because maybe in terms of practitioners are more interested in like having a threshold of the threshold, for example, setting in depth in which they will say, okay, now we need to clean. So they don't want perhaps the millimeter accuracy. They just want to detect if the sediment is big enough or the amount is big enough to send an operator to clean the system. So it's also possible. We are also implementing this kind of solutions currently, which are also less complex, more cheap, these kind of things. So if you remove the accuracy of the estimation, then everything gets much cheaper.
Okay, thank you. So hopefully this answered John Rostam's question. So are there any other questions for Manu in the meantime? We've got a few more minutes in case there's any other questions.
I just make one observation, which is very interesting to see that there's such a difference between the Zurich galleypots and the ones in the Netherlands. This is one of the elements that was of Co-UDlabs, is of course the infrastructure does vary from one country to another, or from one location to another. And this is part of Co-UDlabs was finding out such things and being able to understand how we are able to transfer solutions from one infrastructure to another.
Yeah, exactly. This is very interesting, Ian, what you are mentioning, because basically the focus of the problem, knowing your system could be different, or the way to approach it could be different. So, for example, when we are talking about gallipots, perhaps in the UK, you have an idea on how to handle it. But for example, in Spain or in the Netherlands will be different because the geometry is different. So perhaps what it works in the UK will not exactly be the optimal solution in another part or in another country.
Yes, I remember in a project discovering that Belgium has rectangular manholes and the Germany uses round ones, which was a bit of an issue. I think Alma, shall I? Yes, thanks for stopping. Martin, would you like to share your screen so we can have your slides up?
Yes, of course.
While you're doing that, I was just going to make an observation which ties together all of these presentations. So we started with the CCTV, which is perhaps one of it's the standard method that people have been using. And this is looking in gravity sewer pipes. We've just heard about trying to break new ground with a temperature sensor for sediment levels, and levels of sediment is something which is of great interest to a lot of people. What we're about to hear about is perhaps another one of the basic standard techniques, which is a leak tightness test, which is looking to see whether there is a potential for infiltration or exfiltration. It can be used on brand new pipes, it can be used on existing pipes, or it can be used after there's been a rehabilitation of a pipe in order to see if what has been created is leak tight. But then a quick observation as well, as we've got a minute before Martin starts, is that after the break, we're switching to something completely different, which is pressure sewers. Sewers under pressure, not gravity. And that is a whole different ball game in terms of access and monitoring. Then into another technique you might not normally use, which is the MAX system, putting pressure on the sides of pipes to look at the interaction between pipe soil and looking for points of weakness. And then finishing up with the acoustic assessment, which goes right back to people saying at the beginning there when Joshua was talking about CCTV, is what other techniques are available that we could use. And what I hope therefore is that you can see that across these 6 presentations, we're touching upon many different aspects, all of which potentially we look to coming together in the future. And that brings us perfectly to 20 past, which is your cue, Martin, and thank you. We can see your slides. So over to you. By the way, Martin is doing it rather than Serdar, who was promoted on the on the program.
Yes, okay, thank you, Ian. Yes, I will do the presentation for Seda, as you said, and he has dealt very specific on this topic, and so I will try to tell you what he has found out in his work, and unfortunately he's unable to attend today. So yes, my name is Martin Liebscher. A short introduction. I'm senior research fellow at IKT for over 30 years, and I was the project manager of the part which is our topic here today. So what will I talk about? Now it's gone. So here you can see the structure of the presentation. First of all, I have a small introduction for the reason, the objective, and the procedure, that we have chosen to look at the leak tests on certain wastewater laterals. Second, then we talk about the quality of the test methods under laboratory conditions. And also we had a look on the test methods under practical conditions in our large format test stand. At the end, I will summarize the things we have found out. Yes, so let's start. First of all, I want to say some words to the reasons why we do this project. In addition to the functionality, the stability, and the operationally safety, tightness is one of the most important functions of a sewer system. There is a high hazard potential when pipes are leaking. Exfiltration is not good for the environment, and infiltration influences groundwater levels and the performance of a wastewater treatment plant. We made certain tests on the repair of lateral pipes with shortliners at IKT's large format test stand, and got discussion-worthy results when we test the results of the repair of the repairs. And at the end, yes, we thought at this moment that the test methods, the quality of the test methods is not so good or unknown. Is the best. They are not the best. So yes, what is the procedure for leak tests in a sewer? Normally you close the sewer with a shut-off bubble, then you fill it with water, and while testing you have a look at the water level in certain test vessels. It is also possible to test with air pressure and look at the pressure loss while testing. These are the two test procedures you take with pressure tests. Nevertheless, you also can do it with an optical inspection with a camera. And so you drive with the camera through the sewer, and then you can decide on the condition of the sewer whether it's tight or not. These are the possibilities you have. The objective in this project, yes, we have to identify the error sources and the error rates, how on the different test methods. Also, we have to have a look at the quality under laboratory conditions, also under practical conditions. And at the end, yes, we want to found out some recommendations, which are the influencing factors, the areas of application, and how can you avoid errors while testing. Yes. Yeah, to tell something about the procedure, how we make the I have to have a look. Yes, of course, how we made the tests. We had 3 test setups. On the left hand, you see the first test setup. There we have transparent pipes with adjustable leakages under laboratory conditions. So we can see where is air in the pipe, where makes the company who makes the tests, where they do their errors. And so we can have a look at this. The test setup 2 was for the optical inspection. So you see, we had a setup with major damages, and they were according to the NRW image reference catalog under laboratory conditions. The reference catalog is for finding a preference for repair of sewers based on certain damage scenarios. So you have a look at the pipe in optical with an optical inspection, and then you decide, oh, you have to repair in 1 month, in 2 years, or in 3 or 5 years. At the end, we have our test setup 3. This is made in our large format test stand, and there we have put in 10 times the test setup 2 in our test stand, and then we had a look. Normally, our project was to have a look at repair of laterals with short liners. This was the aim of our project, and therefore we make this test setup. Yes. Now we have a look at the test setup in detail. We have in this test setup 1, we have 3 identical test rigs. You see here we have one for the tightness test under water pressure in this area. Then we have one for tightness test under positive or negative air pressure. And in the front of the page of the picture, you see the part for the visual inspection, because before the companies make the tests, they have to have a look at the pipe, and so this was the pipe they can use to inspect the pipeline. Here you can see sketches of each test rig. The overall length of all test rigs was about 7.5 meters, and there were certain leakages, bends and branches. We simulate leakages due to several valves with different leak diameters. So we can open the valve, and then the pipe is untied, and when we close the valve, it's tight. It's a very easy procedure to simulate such situations. The test rig was an attempt to hide the setup from the contractors, because they don't have to see what they test. Normally, they also not see what they test. The pipeline is in the ground, so they have no possibility to have a look at it. They have to inspect the sewer on the left hand, and they had to do the test on the sewers in the tent. Nevertheless, we were in the tent and could have a look what they do. Yes, here are some impressions of arrows. Left top, you see the wrong application of the water tank. You need to have a look at the water loss while testing. On the right side of the picture, there is a not considered distance to the test pipe. So you need the volume of the test medium, and when you don't calculate the medium, the water, in this distance to the test tank, then you have a problem with the test results. And last but not least, at the end, you see the test bubbles, and there are also problems with these test bubbles. They does leak, and you see in the bottom pictures some examples where why we have transparent pipes, because then we can see where the water goes. This was very important. So what were the results of the tests with the different tests methods? First of all, the leaky pipes. Yes, we have 3 test procedures we have done. We have air overpressure tests, we have air under pressure tests, and we make water pressure tests. And we have seen that there are different observed errors. I don't want to go in detail, but you can see often it was that the sensors does not work as they should do. And sometimes the people, the tester, does things which are not so good because sometimes they don't have the test time. Normally you have a certain time to make the test, and they don't have the time, or they don't beware of constant pressure to make the tests. Nevertheless, it was very interesting. We had these errors, but all 3 test times, 3 tests went very good. On the leaky pipes, you see an error rate of 0% at the air tests, and 15% at the water pressure test. So this was, I think, not so bad. When we have a look at the tight pipes, we can see that also the error rate was 0%. We have the same errors, but nevertheless the errors were there. But the result of the test was okay. So we can say the leak test methods are sufficiently accurate for the laboratory tests. This is very important. At the end, we'll see that it's not so in the praxis tests. Yes, now we come to the visual inspection. We made it at the test setup 2, where we have the sample pipe with major damages for the visual inspection. You see, we work in 2 layers. We have an upper layer with branches, and we have a lower layer. And there they have to inspect it. While they have inspected these pipes, we put a foil on it so that they cannot see what they inspect. This was very, very important. Here you can see some damages which we have applied on the pipe. We have some cracks, shards, vertical and horizontal drops in the pipe, and then also on deflection and angle deflection in the pipe connection, which they have to detect visually. Yes, the results of the visual inspection. This was very interesting. Overall, the damages were recognized. That was not the problem, but we also had a look at the classification rate due to the NRW guideline. And there we have a very poor classification rate due to this guideline. So as a result, we can say that the visual inspection is not sufficiently reliable for our purpose, because we need the optical inspection, and we also need the classification rate to handle with the test results. So yes, we can say an optical inspection is not so reliable. Yes, then we have quality of test methods under practical conditions. Yes, here we have the test setup 3, where we put 10 times the test setup 2 in our large format test stand. The large format test stands have the dimensions. It is 18 meters long, 6 meters wide, and 6 meters deep. So we can make tests in a scale 1:1. This is very important for such tests. And we have also the possibility to change the groundwater level. So we could have a look when water comes in. This was very important because tests are very difficult, as we have seen, and so we could rise the groundwater level, and then we have different typical damages. We have big leakages with really flowing in water. You see on the top left. On the top right, you see a smaller leakage with water coming in a jet shape. On the bottom left, you see a leaking type with drops, where drop water comes in. And last but not least, sometimes we also had a tight pipe after the repair with certain short liners. Here you can see the digged up pipes of the top layer. For us, it was so easier to control the tightness tests, especially with water, because then we can have a look at the pipes outside and we can see comes water out of the pipe or not. And this was very important to classify the tests we made in our large format test stand. Here you see the results. I have to say something to the pipelines we had. I said we have 10 different pipe setups, test setups in our large format test stand. And in these 10 setups, we had tight and untied pipe sections. So we can classify the tests we made by looking at the tight or untied condition. Yes, you see, when we have defect pipes and water is coming out, all test methods with air or with water have a good result. Only one test was wrong, and this is a very good result for such tests. But it changes when we go to the tight condition. The leak tests on the tight pipes were not so reliable. About 13% of these tests have a wrong result. So they test the pipes untied. Nevertheless, they were tight. This is not a problem for the environment, but it's a big problem for the sewer owner, because he has to repair a tight pipe, because the test says the pipe is untied, and then it could happen that the company says, okay, we have to put in a liner, a short liner, or something else. And so it's not a problem for the environment, because the rate that an untied pipe is tested tight is very low. Here we have a look at the visual inspection. There we have to say that the visual inspection was made without groundwater outside. So it was not so easy for the companies to classify the pipe. We could have a look because of the groundwater level. You can see where the water comes in. They don't. They have to classify it only by the optical impression. Finally, the visual inspection is not sufficiently reliable when you have no groundwater pressure from the outside. Then it's not so good to make a visual inspection. Yes, here's an overview of all test methods. And you can see that the leak test methods with air or water, we have different pressures. They were sufficiently reliable, but the visual inspection, there it is difficult to decide if a pipe is tight or not. You can see the damages, but to decide it's tight or it's untight is very difficult for the inspector. Yes, now I come to my short summary. Yes, what are under the laboratory conditions? Yes, we have 97 correct test results, despite of many test errors. Only 4 incorrect test results for water pressure tests. So it's a very high rate, and it's a very good result under laboratory conditions. The leak testing methods are sufficiently accurate. Air testing tends to be more precise than water testing. There you have to know that when you make air testing, it's a little bit difficult to tight the bubble to an old pipe wall. When you under the laboratory conditions, we had new pipes, we have very smooth pipe walls, and when you go on the practical side, it can tend to be more difficult. But under these conditions, the testing with air seems to be better. The visual inspection is not sufficiently reliable because of the deficits also in the classification of damage. Here's under practical conditions. Leaking pipes are regularly detected using leak testing methods. Low risk of wrong test results. So when you have a leaking pipe, you can test it and you will find out, okay, it's a leaking pipe. Tight pipes can be incorrectly categorized as test not passed. And yes, so it is not so easy. You have a wrong test result rate of even 10 to 20%. And so it can happen that a repair is done. Nevertheless, it's not necessary. Yeah, and the visual inspection is not so good, and it's only good to have a look at the condition of in the pipe and to choose a certain repair or renovation method. Yes, now I'm at the end of my presentation. Yes, if you have any question, no problem.
There's only the one question so far. Well, it's not so much a question, it's an observation by Wim saying astonishing. But I wasn't sure whether he was referring to the reply given by one of the previous speakers to a question above, or whether this was a question of yours, Wim. So if anybody would like to add a question into that, please do. Thomas, you have your hand up.
Yeah, maybe Martin, I don't know, maybe worth to mention is how many companies were involved doing this test? Do you remember?
Yes, I think we had about 30 companies which make the tests.
So, and I think Sarah was talking about more than 1,000 tests, is it right?
Yeah, that's right, because
Yeah,
we have different situations when you have a look at our test rig. In the test rig for the practical tests, we had each 3 test lines.
Mm.
And,
Okay, yeah. Just for the audience that they know how big the range of different companies and different tests was for this study. Yeah.
I'm just looking to see if there are any other hands up. I would have a question for you, Martin, which would be, do you have a feel for why the air test was generally was a bit better than the water test. Is there a reason?
Yes, I think the reason for that is very simple, because when you make an air test, you only have to put your bubbles in the pipe, and then you have an automatic procedure in your test facility. You have a laptop or something, and then you only measure the pressure loss. When you have the method with water, you can do both. You can measure the pressure loss, but also you can do it with a certain vessel that you hang on the top of the pipe crown, and then you measure the water loss. And there were problems with measuring these water loss. The vessel has a certain diameter, and when you don't have the right diameter, then you cannot calculate the right water loss. It was or the vessel hangs in an angle. It's not yes, it hangs in an angle, and then you cannot calculate the water loss.
Yes, so I've just seen that as a clarification in the chat from Wim. He's saying there a few years ago there was a guiding rule by IKT, by Sebastian Beck, that a successful test with air can then lead to a successful test with water. Does that still stand?
Normally it is so. When you have a look at the standard 1610, I think, there's the test with water is the last reliable test. So in this test, you have to test with you can test with air, but when you have not passed the test with air, you can make a test with water. Yes. But the thing is, if you make the test with water correct, I think then it's no problem. The problem is when the test is not made correct.
Yes. Thanks, Wim, for referring to the EN 1610, which is the relevant testing standard that relates to this. I'm not seeing any further questions there. And do you have a question for Martin or not?
No. I think
Okay.
everyone probably due a cup of tea.
Martin, thank you very much for that presentation. Now, we are about to have a 10-minute break, which means bring everybody back at 12 o'clock CET. Now, the presentations you're going to hear then, as I mentioned, first of all, this much more difficult issue of how do you inspect a pressure sewer. It is a different situation to gravity. And then the MAX system, and then the acoustics, which are two alternative methods or additional methods that can be used, which are more under development, a little bit perhaps about like the temperature testing that we heard before. So we'll take a break now for 10 minutes. And Ton, if just before we come back at 12, if you could put your slides up, then we'll be ready to go. Okay, see you in 10 minutes to begin. So welcome back, everybody, from the coffee break. And so what I think is going to be an extremely interesting presentation. Over to you, Tom.
Thank you, Ian. We'll do this presentation on the assessment of inspection techniques for rising mains. And we'll have three parts in the presentation. I will give a short introduction, and Irene will tell about the laboratory tests at the IKT that was done within the Co-UDlabs program. And on top of that, we did also a practical test in Arnhem, and Johan Post will tell you more about that research. Well, just a short introduction, the background of the researchers. I think in the Netherlands, but maybe also in other countries, we are in a kind of transition. In the last 10 years, the operators realized that they didn't know actually anything about the rising mains. They did not know where exactly they are, what the condition is, what material it was made of. And we started a program. It's called Professional Wastewater Transport, and we're moving towards to be in control of risks, performances, and costs. And this all put together in the strategic asset management plans. So we try to learn with all parties involved, as well the operators, the consultants, companies which makes inspection techniques, universities, technology institutions. So we all try to put them together and work on different aspects of the asset management of rising mains, starting with the data standardization, and also better understanding who is the owner of which part of the rising mains, and to get back under control of your track integrity to prevent from digging calamities. And when there is a calamity, we would like to learn from it. So we're collecting data on these calamities and incidents. And what we're talking today about, it's about the condition assessment to get better insight on the resting lifespan of these rising mains with the application of a failure risk model. And so far, we have done some publications. I'm afraid they're all in Dutch, but translation is quite easy these days. So we started in 2018 with the guidelines on data collection and the basic techniques like pressure tests and the ground radar. It was followed by a report last year about more advanced technology, about the inline inspections. We make a comparison at the IKT lab, and Irene will tell you about more about this. And recently, I think it's very interesting, we made a model to assess the failure risks. It's a combination of a finity element model to calculate material tensions due to the, how you call it, the weight of the ground above the pipe and the traffic, in combination with the probability of external causes like digging or maybe a failure in operation, and all these probability of failures are calculated together, and the result is for every meter of a rising main, you get a probability of failure during the time span coming. It's still in development. We tested it on 10 rising mains in practice, and well, we got good results, and now we're putting this more in operation and to make it more easy available. I think this will be by the end of this year. That was the introduction, and now we go to the real researchers. One is about the laboratory assessments at IKT Germany, and Irene Scheperboer, currently working at Rijkswaterstaat, will tell you all the details of it. And Irene did a PhD on sulfur acid attack of concrete sewers at the Eindhoven University, and she specialized in condition assessment of wastewater infrastructure. And currently, she works on the condition assessment of major infrastructure in the Netherlands. And the second research in the city of Arnhem with an in situ assessment and a polarization with CT scans of asbestos cement pipes will be explained by Johan Post. He's a consultant at Partners for Urban Water, and he did a PhD on statistical management of gully pipes and laterals of sewer systems, and he has a lot of practical experience and all kinds of researches of urban drainage systems. So Irene, please go ahead.
Oh, Irene, I think your audio is a bit quiet. Still quiet. I don't know whether, yeah, you might plug that in. Alma, are you able to hear Irene, or is it just me?
No, I don't hear her as well.
Oh dear. Yeah, the audio seems to have packed up.
Is it better now?
Yes,
Yeah.
it is. Perfect.
Well, I
Okay.
use headphones.
Right.
Okay. So I'll tell you something about the research done about a year ago at the IKT laboratory, assessment of inspection technology for rising mains. Next slide, please. Tom, can I have the next slide, please? So in this setup, we used a prepared water loop in the IKT large test facility. It was made of steel and PVC pipes of 300 millimeters. And into these pipes, we prepared some artificial damages. I will show you in the next slides how exactly these were prepared and where they are located. And we asked 5 different techniques to do an inspection run in this laboratory test setup. There were 3 commercial participants, 3 instruments from commercial parties that participated. 2 were already experienced and market ready. 1 was near market ready. I think by now they should be market ready. And we had 2 conceptual items from academic researchers. I will not go into detail to these academic tools in this presentation because I believe Professor Horoshenkov will also address these techniques in the last presentation. So we gave each of these technologies some time to do several runs in our test facility, and we would see how well they would perform in such a situation. We had, of course, then a real clear reference situation to which we could compare the results. I would like the next slide, please, Tom, so I can show you the test setup that we prepared. So we had a closed loop, and in the upper series of pipe segments where the damages were prepared. So at our left-hand side, the tools will be inserted. It could be via a horizontal inlet or a T-piece. Then there would be a downward slope of 5 steel pipe segments with several damages applied. In the middle, a quite slightly upward placed part where we had an air pocket installed. And then afterwards, an upward slope of 5 PVC pipe segments, which damages more logically present in PVC pipes. And at the right-hand side, the tools could be extracted from the test loop again. And now I will show you the damages that we applied. Next slide, please. So in the steel pipe, we had several holes installed where water would leak out of the pipes into the open air in the case of the first pipe segment, in red indicated. The holes would increase from size from 0.3 millimeters up to 7 millimeters, whereby the smaller holes of 0.3 and 1 millimeter were in practice quite easily clogged, so they would not leak in the test. So we could not test these. In the second steel segment, we had a deformation of about 6% of the diameter decreased in vertical direction. Then we had in the third pipe segment holes only from the outside, so not holes through. They were all 7 millimeters in diameter, the holes, and had varying depth. In the fourth steel pipe segment, we had decreased wall thickness over a surface of 20 by 20 centimeters and 3 millimeter thick in the middle of these surfaces. And in the last pipe segment, we had the same holes as in the first pipe segment, but then a soil box installed around it, because especially for instruments based on audible sounds, it makes a difference if the water is leaking into the open air or into the sand, which is normally present, of course, around sewer pipes. Next slide, please. So in the middle, we had an air pocket installed. We used a plexiglass pipe segment here, so we could actually visually see the air pocket and control where it was. So the situation was more or less the same for all of the instruments. It was quite difficult to really maintain a tight amount of air in here, but at least we had some visual-based information where the air pocket was, if it was really there, and how big it was. And then the PVC pipes. Next slide, please. Here we had some surface scratches from the outside installed of different depth of these scratches. They were all 50 centimeters long and located different locations. And in the middle, we had an incrustation at the inside made of gypsum. Next slide, please. And then I will tell you about the commercial participants that joined this project. I will call them by name. There were SmartBall from Xylem, LineG from Rosen Group, which was not yet market ready at the moment of testing, and Aquarius of Quaint. These are innovative techniques, and they use different sensoring. All have multiple sensors installed into their tools, instruments. And the question that we ask ourselves is, okay, all these techniques already have some proven value, but which technique fits best for certain purposes, and what can we expect, or what can network operators expect in anomalies, precision, reproducibility. And we did this because the first question was that these techniques are available, they can be used, but asset managers feel lack of independent proven quality of these inspection results. So it's quite expensive to do such an inspection, and they want to be sure that they get value for this money spent. So that is why we started this research essentially. And these were the results. I will not go through all the results. You can read it in the report. I think it's also available in English, or will become available in English in the near future. What we can see from this, I will first explain these colors. So dark green color means that the detection of the anomaly was spot on. So it was the right location. It was correctly named as the defect that was actually there, and it was sized according to the specifications claimed by the companies themselves. Light green means that the defect was there, it was correctly identified, but that the sizing was a little bit off the claimed accuracy. Then we have the yellow color. Yellow color means that an anomaly was detected, but it was not correctly identified as the defect that was actually there. We have blue, and blue is a defect that was registered by the tools, by the inspection companies, but was not intended to be there. Which does not mean that it was not there, but in some cases, so for example, Xylem detected a lot of entrained air in the downward slope in the steel pipes. We did not intend the air pocket to be present there, or small air bubbles to be present there, but it is quite likely that these air bubbles were there because during insertion we had to depressurize the system, and it would empty because of the leaks. So there was a constant refilling and emptying of the pipe, and because of the relatively low water flow velocity, it is possible that entrained air was present in these locations. We could not verify this afterwards, so that was therefore we call it blue. And something similar happened at the joints. So we used some specific clamps to join the PVC pipe segments, and we expected them to clamp circumferentially, but testing afterwards showed that some ovalization was present at these clamps, and that was detected by the tools of Acquaint and Rosen Group, but we could not verify afterwards the size of these ovalities. So that is also something that was definitely there, but we could not compare with the real values. And in the end, there's also some red color, and red color means that a defect was not noticed by the tool at all, or something was detected that was not there. I would like the next slide, please, Tom. So to conclude some of these experiments, I think what very valuable information is to understand that that the techniques are there, and they can do quite some good inspections, especially the techniques with the ultrasonic sensors. They perform very well in locating and quantifying damages in this both steel and PVC pipes. But it is also a question on expectation management. So network operators have to be aware of what they might expect of these inspection techniques and where the limits of these techniques lie in terms of technical or accuracy. And that requires, I think, a discussion or a conversation between network operators and these inspection companies to have a better expectation of these if you let an inspection be performed. And I think we made a good start during these visits at the IKT laboratory. We talked with the network operators. They get a tour, and I think that was real good in educating how you can use these types of inspections. And I think the last conclusion, especially for Xylem, it was a hydrophonic sensor, and in the test they could not locate many of the damages that we would expect them to detect, and that was because of this entrained air that they located, and this entrained air blocks all other signals, so then it is difficult or impossible to detect defects that are behind these air bubbles. So the test setup was not really suitable for this technique. And I think that is a nice bridge to Johan, who used the same techniques in a field study and a more realistic situation, probably. So Johan, the floor is yours.
Thank you. Don, yeah, great. Well, for all my colleagues who say I never go into the field myself, this is me going down a manhole where an air vent is located, which the air vent was quite a lot older than me. So turning it was, well, either a total chaos situation or a nice experience. Well, luckily it turned and it didn't open up all the way. So that was nice. And the right picture is the launching installation that we installed to get these inline tools into the rising main. Tom, can you skip to the next slide? Muchas gracias. So, well, basically after the IKT lab, well, there were still some questions left, even though it already gave a lot of clarity. So there were, I mean, the top picture is from the lab setup, and then the right is the one that we applied the techniques on in the field, which shows how different practice can be from theory. This was a camera inspection that was done afterwards. And basically you have a lot of crust and attached deposits and everything that you don't want in a sewer, but is there in practice. And of course, it's nice to see how these different tools handle these types of realistic scenarios and are still able to give reliable results. But also the fact that, especially in the Netherlands, a lot of pressure lines were made from asbestos cement, which was quite a popular material in the 70s for pressure mains, because it was cheap, available, quite strong. It's still excellent material, even though we don't want asbestos anymore. But it's most of the larger sewer pipes which are used for pressure mains were made from this material. So sewer managers were quite keen to know how these results transfer to these types of materials, and especially also the larger pipes, which are considered to be the most risky pipelines we have. And the other thing that we also wanted to know is, okay, now every water board or municipality is more or less experimenting by themselves with these inline inspections. And it was quite interesting to see what are the practical aspects. What do you need to do as a sewer manager to organize an inline inspection? And can we share some knowledge on that so that you get more realistic cost estimations and you're better prepared in case something goes wrong? So that was more or less the context of this project. Can I get the next one, Tom? Yes. So this was the study area. From the top, from the bottom to the top, there was the launching installation. The little blue thing on top is the entry point that the smart ball needed. I'll reiterate a bit on the different techniques in a bit. And then for the other inline inspection tools, we needed to open the left side and then insert the tool and then close it again, or even remove the entire launching installation and then put it in vertically. But you see every tool has a different approach. And then there was a 1200 meter long pressure line consisting of the pink part is asbestos cement, which was the largest part. And then we also have a small part which was glass reinforced plastic. And then the last part was ductile iron, which was relined later on, which was the picture I showed in the first slide. And also a lot of variation in year of construction, which varies from the 1970s, the asbestos part, to 1997 for the GRP. And the top picture is the flange, which we needed to decouple to extract the tools again. So that's a short overview of the pressure line. It was 1200 meters in total. Tom, can I get the next one? Thank you. But what really made this pipeline unique was the fact that about 90 meters of it was going to be replaced anyway. So that really gave us an opportunity to dig up the pipe, extract different pipe segments, and do some extra research on that. Next one, please. So these are the 3 commercial inspection techniques which were applied to this pipeline. The same ones as Irene mentioned as well. So Xylem had the smart ball, which is the top left one, and then Acquaint had Aquarius, and which is the top right one, and the lower right one. And then Rosen next had their newest generation tool as well, which is the bottom left one, which looks like an exotic torpedo, but went through the pipeline very well as well. Can I get the next one? So if you look at what these different types of tools measure, so we have location mapping. So where's the pipeline actually located, the XYZ dimension. They all do that. Leakages, gas pockets, although because the inspection tools of Rosen and Acquaint either require pre-pigging or are more or less pigs themselves. They do measure gas pockets, but the question is to which extent you will measure them in practice, because they will actually that if you pre-pick it, then you will actually push out any air which was entrained. So if gas pockets are really your concern, then it's the question whether you will actually see them if they're. And then pipe wall thickness, that's something that the smart ball doesn't do. Same goes for angular displacement in joints, the joint width, and the pipe material. Xylem can, with the magnetic sensor, see differences between steel and concrete or something, but not between GPR and concrete, for instance. But I mean, even though the smart ball does measure, doesn't have the same sensors as the other types, it's quite small and easier to insert and extract. So it's really depending on the types of failure mechanisms and measurements you're interested in, which technique you would use, because inserting and extracting the smart ball is a bit easier. Yeah. And for Rose, the angular displacement and the joint width is still something they're developing. So it's coming, but we didn't get the measurements from it in this test. Tom, can I get the next one? Yes. So basically, we set out to answer the question, what can a sewer manager expect from an inline inspection? Well, if you want to define good, then of course we want a good accuracy. So how far is a measurement off from the true value? But also we want a good precision, which I'll call reproducibility in this presentation. That basically means, are we spot on or off each time? If you do an inspection multiple times, will you get the same result each time? Which sounds something like a prerequisite, but of course any type of measurement has some noise. So each time you'll do it, you get a bit of different results. And well, I think the dartboard shown in the slide is always a nice way to visualize that, where the left dartboard has a good accuracy, but a bad precision. So you're near the true value, but you're quite noisy. So every time you throw the dart, it will be a bit off different. The second dartboard has a good precision, so that you get more or less the same result each time, but the result is off, so the accuracy is bad. And well, of course, we want the right one. And then we get a good precision and a good accuracy. Tom, can I get them? Yeah, well, let's look at some preliminary results, because not all the results are in yet. So just like IKT, we also looked at leakages. Only we created leakages on the air vents. So on the right image, you see an air vent which has been modified to more or less be able to preset a leakage with a certain, which we calibrated before they started the test to get a certain flow. And then it flows out on the top, and then it's drained with a pipe to a jerry can, which caught all the drainage water. And then we did this on 2 locations, and because we did multiple inspections, we got 4 leakages, 1 being 0. And then, well, we more or less attuned the flow rates of these leakages to be between 0 and 1.5 liter per minute, which is not a lot. But if you look at the AN regulations, it's quite strict, which is 0.2 liters per hour and not per minute. So if you have like a pressure main and drinking water area, then that will probably be the bar to reach. But one of the problems for this pressure main is that the operating pressure is quite low. Increasing the pressure is not really an option, because then the flow velocity will be too high. And that sort of limits the application of the acoustic sensors which the inline tool uses to detect leakages, because that more or less relies on hearing the outflow of water, which is governed by a pressure difference. So even though you can adjust the flow rate to get this 1.5 liter per minute, for instance, they still might not be able to hear it, because the pressure in this main is only 0.7 bars. Can you do the next slide, Tom? I'm catching myself pressing on my keyboard, but nothing's happening. So basically, if you look at the left part of the picture, then you see, okay, so what does this pressure mean? Well, if you have a rising main in a sloped area, then usually you get a static head and a dynamic head, and that determines your total pressure. Well, in the Netherlands, usually the areas are quite flat, so static pressure, you mostly have a dynamic pressure, which means we have quite low operating pressures. But also in this more sloped area, then you see, if the blue line is the pressure line, you see that near the end, the pressures are also quite low. So that's something to keep in mind. Because if you look at the results in the right table, then for the smart ball, the leakage setup wasn't safe to use yet. So it wasn't in operation, so we couldn't check over there. But both Acquaint and Rose were not able to detect the leakages because of the low pressure, which, well, they more or less stated before we started that it was likely that they wouldn't see it. But even if you have a high pressure main in a sloped area, then it might be the case that at the end where the pressure is quite low, they might not also be able to detect these leakages. So that's really something to take into account if detecting leakages is something you're concerned about. Next slide, Tom, please. So if we're talking about location mapping, then we use GPS mapping as a reference. So basically, the image I showed earlier, the photo where you saw a map where we actually dug up the pipe and extracted several pipe segments. Well, we also use that opportunity to GPS measure the exact location of the pipe and compare that to the different inspections. And well, the Dutch regulations basically said that the horizontal accuracy should be about 1 meter to prevent excavation damage. And what we see the results is that if you apply the same method multiple times, then the differences are about 0.5 meters. But if you compare it to the GPS data, then the deviations are somewhere between the 0.5 and 4 meters, which is, well, sometimes more than this 1 meter that we would like, and sometimes it's less. It's a bit on the. There are quite some differences. Can I get the next slide, Tom? And then we looked at angular displacement of joints. So if you have multiple pipe segments, how are the angles of the joints with respect to each other? If this angle is too large, you might get a leakage. And basically what we did is we used slope profile measurements from a camera inspection. We asked the municipality to do a camera inspection and then extremely focus on getting a good slope measurement and measuring the width of the joints and not so much detecting any cracks or something. Really focusing on getting this slope measurement as accurate as possible. Well, you see a small graph of how that looks from the camera inspection footage. And also a nice thing was to see if you look at this pipe, asbestos cement is quite prone to leaching, I mean. And leaching means that the pipe wall can remain the same, but its structural integrity can still degrade. And if you look at the camera inspection images, then the pipe looks pretty nice. And if you look at the inspection data, then you see it's well, the structural integrity, sometimes about half the wall thickness has degraded. So that's quite a nice difference. Can I see the next slide, Tom? So if you compare these slope measurements from the camera, which are the horizontal axis, to the inline inspection results from Acquaint, and you look at the angular displacement, which they both computed, then you see the diagonal line is the line of perfect agreement. Then you see that more or less the trend is the same, but the absolute values are a bit different. But of course, camera inspection is also not a perfect reference. But to put it a bit in perspective, the maximum tolerance for this diameter pipe is about 3 degrees, and the precision, so the uncertainty in the measurements due to noise, is about 0.41. So that's quite in the good range. So that seems to be acceptable, and also the general trend is the same. So the camera inspection and the inline inspection more or less agree on the angular displacement. So those results are quite nice. Can I get the next slide, Tom? And to get more of a reference measurement for the wall thickness, we decided to extract several pipe segments from the pressure main, and then transport them to the CT scan. And what the CT scan basically does is it's an X-ray tube that turns around, and then you get different slices, and then you get a measure of the density, when a light part of the image is high, that represents high density, and then the darker parts are lower density. And if you have parts of the pipe which are leached, then you see that as a lower density, because the calcium has more or less dissolved. But this also brings one of the limitation of the CT scan, because the CT scan is more or less made for human body. So in the software, there are all kinds of tips and tricks to more or less optimize the imagery for human tissue, which is hard bones and tissue on the outside and soft tissue on the inside. So this also gives a bit of weird phenomena, because it tries to more or less also use that philosophy on the asbestos cement pipes, which we inserted. And that gives some anomalies in the middle of the CT scan. Tom, can you show the next slide? But getting the pipes into the CT scan was already quite difficult, because it's asbestos cement. You're not allowed to cut it, and it didn't fit into the CT scan in one piece. You're not allowed to transport it because of regulations. So we had to get an exception from the regulations. We had to build a special depressurization chamber to cut the pipes into pieces which would fit, and then label those so we could map them afterwards, and then transport them to the TU Delft. But luckily, that all went fine. It only took about half a year of preparation. Can I get the next slide, Tom? Well, we only got the results about 3-4 weeks ago, so I didn't perform the full analysis yet. But well, if you see some leaching, then the material is less dense, like I explained. And if there's really corrosion, then the material is simply gone. Can you show the next slide, Tom? Yes, perfect. So the red line is more or less a cross section from outer wall to inner wall from a part of this pipe. And then you see the vertical axis is the density of the material in house-filled units, and the distance in pixels from the outside to the inside of the wall. And then you see that, especially on the outer wall, there's not really any leaching. And then you see the density is about 1400 HU, pretty constant. And then suddenly at around 30 pixels, then you see a quick degradation. You also see that in the image on the left, it's just a little bit darker. And that's the leached part where there's less calcium, and then also the structural integrity of the pipe is more or less less good. And in the middle of the left image, you see these weird artifacts, these bubbly things, which I was talking about, that the CT scan software is trying to more or less put it into the constraints of a human body, and that gives some in the middle part some weird anomalies, which we are now correcting for. Can I get the next slide, Tom? Well, of course, the CT scan results were only quite fresh. So we did do an initial data exploration, which shows some promising agreement with the inspection data. So most likely it will be okay, but of course we're still doing the detailed analysis. So I'm reserving some conclusions for now. But I hope soon more results will follow. Tom, the next slide, please. This gives some impressions of everything you need to get this type of analysis, especially CT scan part. A lot of parties involved to get it done, but a special shout out to the municipality of Arnhem and of course STOA and Rionet for making this possible. And the inspection companies Acquaint, Xylem and Rose for participating. That was really really nice. That was it.
Thank you very much. Yeah, and that was really very interesting. Well, the whole thing, to hear the reasons why is this needed. And I would reiterate what Ton said, is that most countries just a few years ago knew very, very little about their rising mains. Some of them know a little bit more, but this is something of interest worldwide. And fascinating to see how the laboratory work through Co-UDlabs, which was more like a pilot, is now being further explored for real. I'm just looking, there isn't a question in the chat for you. Alma has pointed out that if you want to know more about the Transnational Access Project, the one that Irene described, that is available on the Co-UDlabs website. There is a summary of the findings of that. But yeah, and I was just, my question I think for you would be, what next? What's the timeline? When do you, and are you intending to publish this? Where are we going with this work at Arnhem?
So we're I'm expecting to finishing up within a couple of months, writing the report for the Dutch sector, and then I mean also out of personal curiosity, I'm also quite keen to publish it internationally, so that I mean I think it's very important that we also share this knowledge internationally. Because for a large part we all have the same challenges in and I think this knowledge is applicable everywhere, and we're also trying to figure out what are still other questions coming from the sector. So should we apply a similar approach or experiment to different materials or different diameters? And see whether inspections which have been done 5 or 10 years ago, and if we re-inspect them, do they still give the same results, or what would be a good frequency of inspection for pressure mains? Because now we've only just started doing these types of inline inspections.
Thank you. And with only about half a minute to go, Irene, have you got any observations on, having done the lab work and now seeing what Johan's done, any particular observations about what you've seen with it being taken to reality in Arnhem?
Well, I thought it was quite remarkable that a leakage test was so difficult to perform by the inspection techniques in situ, because we know that the inner pressure is relatively low in pressure sewer mains compared to drinking water pipes. But still, leakage is one of the most important defects that network operators are interested in. And yeah, I thought it was quite remarkable that it's still so difficult to detect these leakages. It's important to realize that a network operator.
Well, thank you, all three of you, for a fascinating presentation there. And Ton, if I could ask you to stop sharing, and for Mark to start sharing for his short presentation about the use of the MAC system. So, Mark, are you able to share your screen and also your video? Oh, excellent. Don't think we can hear you yet, Mark.
Yeah,
there
I'm
you
sorry, I'm a bit on delay. I just broke down my bureau and I only had to fix something. Can you hear me?
Yes, indeed. You're on.
Yeah, you see my screen?
Indeed, yes.
Very well. So, yes. So we can start right away. Thank you very much for having me today. As you can see on our timetable, we are talking about the Mac system now. And from what I've heard today, this matches pretty well with everything else. This morning we have been talking about visual sewer inspection, and now I would like to present to you the Mac system. Yeah, Mac is not the abbreviation for the North American fast food industry, the Big Mac or whatsoever, or the faculty where Simon Tate is working. No, it's the abbreviation for Mechanical Assessment of Conduits, and it's a non-destructive testing method for the assessment of the structural integrity of accessible sewers, which means sewers that are wide enough that you can walk inside, and these are posing the high risk asset we have in our streets, where possible failure might have catastrophic consequences, and that's why we pay special attention to these ones. The Mac system has originally been developed by Olivier Thibault like 35 years ago. Olivier has now retired. He was working with Eau de Paris, that's the sewage treatment department in Paris. And the French apply this, like, as I said, for more than 30 years now, and they do an annual testing of more than 40 kilometers in their sewers each year. Before I go into detail about what the Mac precisely is and how it works, it can be considered as an add-on to the regular optical inspection that you do. Yeah, you go through the sewer and you say, oh, it looks good or it looks bad, but it's just the negative impact is it is just an optical inspection, and from the optical inspection you sometimes cannot precisely derive whether or not it's really structurally sound. The whole thing arose from a cooperation between Eau de Paris and the IKT, so we helped them in improving their device, and they in return provided us the working principle. By that time they still had a patent on it, and we were given this procedure where I did my PhD about. So the operating principle is actually very easy. The whole thing basically consists out of a hydraulic press that is installed in the sewer system and is pressing into the sides of the sewer, which you can see here in the working principle. And what is being measured is force over displacement, some kind of stiffness from the overall system, the structure itself and the surrounding soil all together. And on the second figure you can see that we install several transducers in a certain pattern so that we can not only detect the deformation of the system but also the deflection the system exhibits in the longitudinal direction by transmission ratio as a second parameter. The whole system is applicable in various profiles. Circular X-shaped mouth profile doesn't actually matter, and you can apply it, as I just said, from DN 1000, which is accessible, up to dimensions of more than 2000 mil. Well, the largest we have ever tested was 2600. Materials, concrete, brickwork, synthetic, doesn't also matter. It can adapt to everything actually, and it's an absolutely non-destructing testing device because the force is limited. So even though you're pushing into the inverts, you're not destroying anything. The force is limited and the displacement you reach is also limited to a few hundred microns. So that is all happening in the purely elastic range of the system. And on the right hand side, you can see my colleague Marco with the system installed in an X-shaped profile. And the system is also adaptable to different sizes. Here we have the system installed in a brickwork sewer of more than 2000 millimeter in the municipality of Hamburg. You can see this is a huge diameter, shallowly covered, and is a high risk asset, should not fail under any circumstances and need special attention. On the low right hand side is the additional feature. We improved the original Mac from the French with. This is also called handheld. The original version was cable driven, and it is quite convenient working in confined spaces when you don't have so many cables around and everything is wirelessly controlled. How do you proceed in the sewer? Well, you choose a certain pattern of spaces where you apply the system. This is usually like every 5 to 10 meters in the sewer, depends on the condition of the sewer, of course, and you position the transducers in a certain pattern around the press, like 50 to 100 centimeters, to detect the displacements. And you're usually doing 3 testing cycles. The first one is to properly fix the press at the wall. The second is the actual measuring procedure, and the third one is to determine whether it gives the same results as the second one. For planning and preparation, of course, you need to see plans and reports of the sewer you want to examine. You can also do preliminary finite element calculations to see or to estimate the lower and the upper boundaries of what to expect, and not to overstress the structure. This is an extra part I have left out today. I'm only referring to the pure working principle of the machinery. What you of course have to do is the general things you need to do before you enter confined spaces, especially sewers: securing of the entry side, securing of the exit side. You need to vent the sewer so nobody is potentially suffocating down there, and you can do the optical pre-inspection to see if there is no obstacles in the way for the machine to pull through, because it has some like 100 kilos and need to be operated by 2 people. So if you have obstacles in the way, that's not so good. The time frame. So let us see an example for typical one-day tests in an X-shaped profile we once had in a DN 950 over 1400. Typical examination length per day you can do with the device. It's also depending on the condition of the sewer. The worse the condition, the slower you usually proceed. Well, that's a result in itself already. And you can do like up to 250 meters per day. Sorry. And do like 15 to 25 measuring points in a single day. Well, this all depends on the sewer condition. And on the bottom side, you can see a typical time frame. You need like 1 hour for preparation. During that time, you can do the optical inspection of the sewer if you have not already done that, or you should have done. You need about 1 hour to install the device in the sewer. You have a general width of 600 millimeters in Germany in the manhole entries, and you can disassemble the device into like 3 or 4 bigger portions that is being reassembled down in the sewer. Then you take your measuring like 4 or 5 hours, depending on how long it takes, and another 3/4 hour in general to remove the system. This goes a bit quicker because you don't need to arrange everything properly anymore. You just need to get it out. And later on, very conveniently, you can do your assessment of the data you have gained from your sewer back home in the bureau. And how does this potentially look like? We can see here a typical result from a MAC test. We have the two variables, the max stiffness and the transmission ratio, where I would like to refer only to the first one. The second one, the transmission ratio, is another variable that is necessary for the fillet element calculation as a comparative result, which I would like to spare you with due to time constraints here. So in this example, you can see that in the first half of the sewer, you have quite a high, don't know if you can see the mouse pointer here, you have quite a high max stiffness, while it's dropping down suddenly in the second half. So you can split up this one into zone 1 and zone 2, while zone 2, even though it does not look any different, it apparently is weaker in response than zone 1. And you can also find some very weak spots I've marked out here, which are potentially points where you can say that you are taking drilling cores here, while otherwise in the purely optical inspection, you only have the chance to randomly choose where it looks bad and say, okay, we take a sample here, but you can never be sure. The MAX system can explicitly tell you where the best spot is to do so. In the end, you can derive from the picture before a so-called quality index of the sewer. This is just a recalculation of the E-modulus of the wall of the sewer in relation to the theoretical new condition of the sewer, where you can say in this example, okay, it's considerably dropping down here from like 50% down to 20% in the course of the examination length. This is a typical example you might have from an examination. So in all the results of the MAC testing, the mechanical part would be like classification of homogeneous sections of the sewer, uniformity of the pipe soil system, which can be done by assisting means of finite element calculations. You may detect weak spots in the wall, and you might therefore determine extraction points for taking core samples, for instance. By separating pipe and soil stiffness by means of statistic FE calculations, you can determine the E-modulus of the pipe and the soil and use these as entry values for like A127 calculations for trench laid pipes, or for calculation for CIPP liners as well as additional information. The results from the MAC test may also help you in choosing the right rehabilitation for your sewer. Maybe you don't need to do anything, but it may also help you in determine zones in homogeneous sections where the sewer has like hose pipe condition 1 or 2. Is it correct or is it not correct? And can help you in choosing what are you aiming for. Are you aiming for preservation of the substructure, just sealing off leakages, improving of the hydraulics, or soil improvement? And that's where the system may help you with. Quality assurance, yes.
We've reached time, but I can give you a couple more minutes. I see you've got 3 slides left.
Yeah, I'm ready in a second. You can also use before and after test with the MAC. So doing the before test before the rehabilitation method applies, and a second run afterwards to see how good the impact of your rehabilitation was, which is indicated in the slide here, the red line before working, or the green line after grouting, or even doing an additional shotcrete on the wall. As I said, there's actually two parts of the MAC system. What I've showed you here today in brief is the functioning principle of the MAC test itself. The second part, which I would need another 30 minutes to explain for, maybe a bit too annoying for today, is the back calculation to narrow in the results and to help interpreting the results. And point 3 is then calculating the structural safety for the system. So last slide, the MAC system altogether helps you in detection of weak spots in the sewer, helps you in finding out the rehabilitation method. You can then monitor the rehabilitation process. In the end, verify whether rehabilitation was okay or not, and you can also, by continuously over the years repeating examinations, see how the long-term effect is in order to properly point your financial means that you need to introduce into the sewer. So that was my run through for the last 15 minutes. If you have more questions, please now or maybe later. I'm not out of the world. Thank you very much.
Thanks very much, Mark. And I did see you had the shortest time was allocated for you today. So well done for covering all of that as quickly as you did. If you would stop sharing. So I think we're on to Kirill now. Alma, do you want to introduce this last session?
Yes, well, I'm also looking at the panelists. I cannot actually see Kirill online yet, so I guess we can take a few minutes if there's any questions so far. To Mark.
Kirill did say he would have to dip in and out because he had.
He did, yes, because he
teaching.
had teaching. So I'm guessing he might just be having lots of students asking him questions.
And if he does not attend, I was just wondering, can either you or Simon do his presentation?
Yeah, very much appreciated, Wim.
Yes.
Yeah, Ian will send Kirill's presentation to Simon just in case, so he can present for him.
Thank you very much, Lindsay. You're sounding very ethereal, as if you're it's an interesting echo.
It's because Simon and I are in the same room.
Oh, right. Hence the echo. Okay. Well, Simon, if you want to prepare in case Kirill doesn't come in the next 2 or 3 minutes. So we have an opportunity if there are any questions about what Mark was just saying. Looking in the chat.
So say the chat's got a very exciting message from
gosh, yes.
Last summer a MAC test saved us several million euros. So that is, thank you for sharing. That should be very interested for everybody else interested in this technology.
Yeah, it's not always about selling stuff to people, but also that's what the MAC test may also give you proof for, is that maybe your system's just not looking really good. It's just a messed up car that is technically okay, but not looking so very fine. But in the sewer, hardly anybody cares, and that is also a result that may derive from the testing.
And I can see Tom Benen has his hand up.
Tom,
you have a question?
Yeah, I have a question because in the Netherlands we have a lot of small sewers, and I was wondering if there are any ideas about robotizing this kind of test, so you don't need a man-accessible sewer, but if you can just pull in some kind of robot who can perform the test in the smaller sewers.
Yeah, we are precisely working on a smaller system that is. I have noise in the background.
Oh, yeah, time.
Yeah. We are precisely working on a small scale system. It's not yet robotized, so you need to push it in and out by extension of rods.
Bit confusion with the European and UK times, unfortunately.
Simon.
So I'll get started, and then Kirill will join us presently.
Okay.
Yeah.
Simon, we'll just let Mark finish his question, then we'll get on with you.
So yeah. I'll just get the presentation up, and then we'll get started.
So Mark, you were explaining
Yeah.
your advertising.
And also, we last year have invented a so-called micro Mac, which goes from DN300 up to 600, and has actually the same basic functions than the original device, but it's more related to the installation of CIPP liners to check whether the installation was successful or not. Please understand that a miniature device has only limited capacity in applying force on the walls, and so. But if you're interested in that, you can get back to me. I can tell you more about this. So that was
Thanks
my
very much,
30
Mark.
seconds.
And I think
Just
we're
about
now.
to get started.
I think we're now organised with Simon starting the presentation, Kirill joining. Is that right, Simon? If you want to share screen, Simon.
Okay, right.
Thanks. Screen's up now.
Everybody able to see the presentation?
Yes, yes.
Okay, so apologise for this, as I say, a bit of time delay between Europe and the UK. So I'll start for the first few slides to give you some idea of what we've done in Pipebots, which is a large UK project, which main aim was to develop acoustic robotic platforms to do autonomous inspection of both sewer and water supply pipes. And part of the project was to look at developing different types of sensing techniques. So, presentation split into four. Talk a bit about the background of the work, different acoustic inspection methods that were examined during the project, and then give you some information on what happens when you put a sensor effectively on a mobile inspection platform. And there'll be some comments at the end about the future of in-pipe robotics. Okay, Kirill and I, we've been colleagues for quite a long time, about 2 decades. So we've worked together looking at using acoustics for various measurements in pipes. The reason why is acoustics are a bit like bats. So you transmit a particular type of acoustic pulse, and that could have a single frequency or multiple frequencies, and then you listen for the reflections. And if you have a multi-frequency pulse, then you get a lot more information than a single frequency pulse. So you can see on the left there a sewer pipe with some water in the bottom of it. The reflections that you get reflect what's actually in the pipe. So you get reflections from the roughness on the water surface, reflections from the joints, and also reflections from defects within the pipe itself. On the right-hand side is one of our mobile sensor platforms, and you can see our more modern type of acoustic sensor design. So in the middle, the silver disc is a loudspeaker. And then if you look at the hexagonal green part, then the hexagonal green part is 6 microphones. They're very, very difficult to see. They're the small silver squares that you see in the middle of each hexagonal size. So that's the size of a microphone that you would get within your mobile phone. And that's typically the type of technology that we use. Mobile phone microphones are extremely good, very high fidelity, and very low cost. The sensors on the outside in the round band are just a ring of ultrasonic sensors. The other reason for using acoustics is it's very, very low power. We talked about videos, CCTV earlier on today. CCTV needs images, needs light. Acoustics don't. They use maybe 1,000th of the energy that you need in a visual inspection technique. So you can run your sensor for much, much longer or use much, much smaller power sources. So key research challenges when looking at acoustic inspection are you get multiple modes when you propagate waves in a pipe. So the particular frequency, you might get a wave that moves down the pipe that's perpendicular to the axis of the pipe. These waves are very simple to analyze because they move down the pipe, they're undistorted, hit something and you get a very simple reflection. Fortunately, typically when you go to higher and higher frequencies, which give you more and more information about your defect, then you don't get this plane wave mode, but you get a mode where the acoustic waves bounce backwards and forwards all over the pipe, and you get this multimodal propagation, which is much more difficult to analyze. The advantage of this higher frequency propagation is that it's able to pick up defects with much more fidelity. Also, with some any wave sort of process, the wave itself disperses as it hits joints, lateral connections, imperfections in the pipe itself. So issues such as wall roughness, that reduces the energy in your reflection. As I said before in the slide, that the acoustics feel everything inside the pipe. So they feel the pipe wall, they feel its joints, its defects. And as with sewers, if you've got a water level in it, it feels the roughness of the water level as well. Now that can be an advantage because it also gives you information of whether the water level is changing or not. Scattering from artifacts can be an issue. So if you look at the pipes we typically tend to look at, you tend to have regular joints. So as you get reflections from the regular joints, then the signal loses some of its strength, but you also get interactions between reflections caused by different artifacts. And of course, you also get the effect of the robot itself. So previously in our earlier work, we'd sense a sound source and some receivers at a static point. But if you're looking at sort of autonomous in robotic inspection, then the robot has a form, and that form causes reflections as well. So ideally, as you have a robot moving through a pipe, you want to be able to remove the effect of the robot itself. So what this shows here is what I've been talking about. So at the lower frequencies, you have this sort of brown round circle at the top. So that's a plane wave mode, where you have the wave moving down the pipe with along the axis of the pipe, and you get a very, very uniform signal being returned. If you start looking at the higher frequencies, so you can look at F10, 20, F01, what you tend to get is with the different modes that you get this more complex spatial shape. And that complex spatial shape needs to be analyzed if you want to get the information from the higher frequency. Okay. I've just been told that the expert has returned, and you no longer have to have the sort of simple water engineer talking about this, but I think Kirill will take over the presentation from here.
Simon, you were doing such a good job. I was I think you're doing so well about this.
I think you're still muted, I think, are you?
Can't you hear me now? People, can you hear me?
Yeah, I can hear you.
Yeah, your microphone's not working.
Alma, can you hear me?
I can hear you.
So everybody
I
else.
think everyone else can hear Kirill. Simon, it's just you.
This is what happens when you work with a professor of acoustics. Things like loudspeakers and microphones never seem to work.
Simon, people can hear me.
It's only Simon.
Yeah, okay.
I think Simon maybe switched off his sound.
Simon, you switched the sound off.
Yeah.
Anyway, Kirill, do you want to share your slides so you can?
I think
it's me,
Simon.
I've turned the loudspeaker off because we were getting double echoes.
Oh, okay. Simon, look, I'm just was saying you're doing such a good job. I didn't want to disrupt you. So honestly, we're covering it perfectly, absolutely perfectly. So if you want me to take over, so that's fine as well. We can do it together anyway. So
yeah, probably better if you take over. I'll stay on.
okay, okay. Let me have a look if I can share my screen with you people.
Yeah.
So okay. Sorry. So if I share, and I really apologize. I didn't realize it's a time difference. So I was actually working on the fact that it's 1 o'clock. Okay, can you see that?
Yeah.
Okay, so what Simon was telling you about is exactly right. So this multimodal propagation makes analysis of signals in pipes much more complicated. What you see in this picture, so for example, if the wavelengths of the sound is much greater than pipe diameter, it's a top picture. You look at the distance, which is the time multiplied by sound speed in air. So that's the amplitude, and you can see the signal actually reflected from artifact, like at blockage. It's very simple. But as the frequency of sound increases, so further away from the point when the wavelengths become comparable or smaller than the pipe diameter, so then the complexity of the signal increases proportionally. And then it depends where you put the microphone. So if you put the microphone on the top, for example, you get red lines. If you put microphone on the bottom, you get blue lines, and also instead of just one simple arrival, so you get two arrivals, so more than two arrivals. And the reason is because the sounds become dispersive, so they travel at speeds which depend on the frequency. And that requires some analysis, which is actually quite sophisticated. And we actually developed algorithms to make this analysis useful for being for working on robots. Another problem is the wall roughness. So a lot of pipes are inherently rough. Concrete pipe, an example, so it has a rough wall, rough joints, and so on and so forth. So as a result of that, actually, if you look at the relationship between similar what Simon was showing you on the slide before, penultimate one. So if you look at dependence of the wave number on the frequency, in the smooth pipe, you find that there are a few simple curves which always are in the positive domain. So in rough pipe, it's just much more complicated. You also got curves which extend to the negative domain, and that means actually there are some scattered waves will propagate from the roughness in the backward direction, and also they propagate with the speed and attenuation, which is quite different to that found in the smooth pipes. So we developed models which can predict that, and this model is computationally very efficient. So you can deploy them on the Raspberry Pi or something like that. It's a simple processor which goes onto the robot. So this effect can be accounted for, and we need to do that to make sure that robot works in the pipes which are realistic. Another problem is a water level effect. You can see in this picture there is a always water level in the pipe. It's not very high water level in gravity-fed sewer, but it is a water level which makes pipes asymmetrical. So as a result, this asymmetry reflects in the model patterns, which Simon mentioned in one of the previous slides. So these modes begin to split. Effectively, the frequencies of the modes actually so no longer single. So some of the modes, they actually bodify and they split into different frequencies. And as a result, effectively, we increase the number of modes which can propagate in a pipe like that. And this effect also can be accounted for. It can be accounted for by using more computational demanding model like COMSOL, but we also just develop algorithms which are very computationally efficient. They're based on approximations, so they can be deployed on a simple processor like Raspberry Pi to take into account. And this picture actually shows the example of that. So the left figure, it's actually when there's no water in the pipe. So H is the level of water, A is the radius of the pipe. And that's the wave number, that's the frequency. But as the level of water begins to increase to 0.1, 0.2, you see actually the modes begin to split. So those curves actually no longer a single line. So they actually they take two different lines. And that's actually quite peculiar phenomena, which we accounted for analytically. So another thing as well, so we look at microphone arrays. So with a single microphone, as I showed you previously, it's quite dangerous to take measurement because you don't know where this microphone is and what, in this case, mode you pick up with this microphone. If you use microphone array, like for example, showed in this picture with 6 microphones connected to Raspberry Pi, so we can combine signals from different microphones. And also we can use some kind of fancy compressive sensing to clean up the mess, which you usually obtain in the signal recorded with one microphone. So to make the signal look much more clean. And that's very useful because in this case, you can take a signature. For example, this one comes from the end of the pipe and make analysis of the signature, very computational efficiency, about 100 times more efficient than visual images. So to detect what it is, whether it's pipe end, lateral connection, or a blockage. And that's the slide shows you the principle behind it. You see these signatures all different, whether it comes from a blockage. So signature from blockage looks different to the signature from lateral connection. So signature from the elbow looks different to the signature from lateral connection, and signature from a robot in lateral connection looks different to the previous two. And we have computational models to account for that. We developed that as a part of this project. I think I talked about higher order modes, but one thing we found as well. So with the higher order modes, just look at it. So we can actually make use of those higher order modes to understand where the artifacts are in the pipe with respect to the angle, whether it's on the bottom of the pipe or on the top of the pipe, on the left or on the right. So, and for this purpose, we use actually signals obtained on different microphones in the circular array. Yeah, maybe just for saving time, I just skip it. But basically, I'll show you the picture, so how we do it. Effectively, if you look at this picture, this is the distance in the pipe. This is the degree in the pipe. So starting, I believe, from the microphone 6, which is a horizontal distance. Actually, this is the angle going like a anti-clockwise direction. So by using the combination of different microphones in the 6 microphone array, so we can actually tell where the artifact is in terms of the distance and where it is in terms of the angular position in the circumference of the pipe. So those red lines correspond to different degrees at which the lateral connection connects to the pipe. And that's very useful for the route planning, for the actual the robot. So because robot would know far away from the artifact where the artifact is and what is actually nature and where about in terms of the lateral, so in terms of the angle in the pipe it is. One thing actually we found very novel in this research is actually making measurements on the mobile robot, because stopping the robot each time, so it takes time, and also it reduces the speed at which the survey is carried out. So what we did actually, so we developed algorithm, and it's patented algorithm, so where we actually can compensate for the mobile movement, so mobile measurement of the robot. And actually that's quite useful because not only it allows measurements to be done on the move, but also it allows to separate reflections coming from the front of the robot from the reflections coming from the back of the robot. And also it allows the improve the quality of the analysis. So in terms of the identification, what it is, which reflects the sound, whether it's a pipe end or lateral connection, whether it's in front of the robot or at the back of the robot. Okay, so last one probably in years. So we also previously I mentioned that we used all these things on the circular array, but we realized actually in some modifications of the robot, it's nice to use a linear array. So in this case, we developed similar algorithms to be used on a array, which is basically a array of microphones attached to the top of the robot or on the side of the robot. And with this arrangement, we can also do exactly the same what I showed on previous slides. We can do mobile compensation, and we can also do the separation of the reflections coming from the front of the robot from the reflections coming from the back of the robot. And that actually now been implemented on the minicam robot, which we building in collaboration with Northumbrian Water and Minicam. Just briefly before I finish, I show you the timeline for pipe boats in terms of robotics. So those ideas which Simon and me talked about acoustics, we wanted to implement on the actual real robots. And we started first in 2020. We put first of the acoustic sensor, you can see loudspeaker here, on a sprint boat, which we built first in 2020. Then also we put a microphone on a little joy, which can go into very small pipe, about 75 millimeter in diameter. Then also we put microphones and a loudspeaker on a skateboard robot, which we built in June 2023. So we also built a robot called Kanga. So this robot is a collaborative robot. So we built more than one of those, and they can actually team up together. So one of them can send the signal, another one can record the signal, and then we can actually make them analyze the signals collaboratively rather than when the speaker and the microphone are co-located on a single robot. Also, this robot actually can rescue other robots. So by finding them in the pipe using sound signature, go into them, picking them up and dragging them out if they failed. Now we're working with Minicam, as I mentioned, so we're putting the ideas on the commercial robot, so which is robust enough to go into real sewer pipes, and that's work will be extended to 2026. Simon, do you want to talk about the industry uptake? You're on mute, Simon.
Right. Yeah. So for those you're not in the UK, we have a 5-year asset management planning cycle that applies to all our water companies. So it affects the sort of uptake of innovation in that we are just moving into asset management period 8 in 2025, starts on the 1st of April. So typically what you tend to see with companies is they adopt new innovations in the middle of the asset management cycle because it's in their asset management plans, and then at the end of the cycle they start to consider what they're going to do in the next one. So particularly for us in the UK, we have these sort of green years where companies pick up innovation, and the orange years where they're thinking about it and writing their asset management plans. So just to make people aware is that we tend to get bursts of uptake and then periods of quiet and then periods of uptake again. Harold, do you want the next one?
Yeah, and they'll say something about pipe boss blockage, Simon.
Yeah, so one of the issues in the UK is we have a lot of issues with intermittent blockages in sewers, and it causes sewer flooding to properties and also premature discharges from overflows. So we've started a project the end of last summer with a water company called Northumbrian Water, based around about Newcastle, and we're looking to take a Minicam robotic chassis, as Kirill says, put on the sort of, you can see the linear sort of microphones on the robot, as well as a camera, and that robot is being built at the moment, and it will go into a field site, and the idea is that the robot will patrol a certain few hundred meters of pipe for up to maybe 30 days, looking for blockages and then reporting back the size and the position of the blockage to the water company, and then they'll make decisions about whether to go and clean the sewer or to leave the blockage where it is. Or it may disappear because of a heavy rainfall event, and then the robot patrolling about picks up the reduction as well. Okay.
Just one last thing on the slide. Well, what we're working now, so acoustics on its own is not good enough, because ideally we'd like to map the pipe to greater detail. So therefore, we begin to deploy plurality of sensors, like traditional video camera, but also LiDAR, which produce a really high quality map of the pipe. And that takes us to the next, I think, penultimate slide, which is to do with the future of in-pipe sensing. And that's actually to do with the combination of several sensors, or in sensor fusion. So that will be done as a part of European Union Pipeon grant, which Simon and myself starting this month in collaboration with people from Europe and led by Tallinn University of Technology. And the objectives of this particularly work package we're involved in to develop new hardware to provide the robot with plurality of senses, not just sound, not just visual, but other things such as underwater penetrating radar when the pipe is flooded, and optical sensing. And this can be used for not only detection of the artifacts, but also for the mapping and navigation. So anything else to say about the slide, Simon?
No, I think that's fine, I think.
Okay, and we are open to collaboration. If anybody from Europe wants to know more about PipeBots grant, you go to their website, but also there'll be the website for PipeOn grant. And you're welcome to write either to myself, to Simon, I didn't put your email here, so, or our schooling. So we're happy to talk to people about this work in more detail. So did you say about collaborative nature of this grant, Simon, PipeBots, about University of Birmingham, Bristol Elites?
Yeah, I did say that it was a multi-university
Okay.
grant where we
Okay.
took skills from the different universities,
That's
but
good.
Sheffield has a particular skill in the
Good.
sensing and particularly acoustic sensing.
Look, thank you so much for listening, and I'm really sorry I'm completely messed up the timing. But Simon, thank you so much.
And
for
that's
picking it
okay.
up.
Yes, thank you, Kirill and Simon. So are there any questions
That was
from
very
anyone in
competent.
the audience? And also I see we have reduced somewhat the number of attendees, so please feel free, either put your question in the chat, and I suppose if somebody wants to talk, just put up your hand, we can unmute you. So we now come to like a general discussion. So if there's any questions on this or any of the other presentations or any general comments, please feel free, or just anything you want to share.
I suppose I would just say, hopefully you've now been able to absorb all of this variety of presentations that we had. And I suppose I would say as well, for any of the speakers, if you've got any final observations you'd like to make from what you've heard this morning, or questions that you have for other speakers.
I think we've got a question coming in the chat,
Good.
which is a good one for Kirill and Simon. And I guess their collaboration now as well with the water company with the last slide. So are PipeBots more than an academic toy? Good question.
It is, Simon, do you want to say that?
Well, I think it is more than an academic toy. I think obviously we've had a lot of funding from our research council, which is very academic focused. But we now work with the vast majority of the water companies in the UK. And we have talked to 1 or 2 water companies in Europe. And you can see with the PipeBot Patrol project that we're moving from the university lab out into a more practical situation. It's not a system that's commercially available or commercially ready yet, but the project, the blockage project, will have a prototype that will operate within a system for 30 days. Okay, it only will do blockages, detection and size and position, but it's starting to use aspects of the academic work in a much more practical environment.
Well, the sensing and mapping technology which we developed as part of this project are in great demand now. So there's several water utilities, including Thames Water and Northumbrian Water I mentioned. So they want to see that working in real pipes, pressurized rising mains, and gravity-fed sewers. Also, we discussion with the American company now, so who are building robots, and they're very keen to try to reproduce our small robots I showed in one of the slides, particularly Joy and Kanga, which are small enough to go in 100mm diameter pipe and work autonomously without tether. So I think that's probably a longer term job, but we believe actually by the time it's AMP9, Simon,
yeah, so
we'll see that in real pipes as not a toy, as a real solutions people can trial. live in the pipe and forget about them for a while, for at least a month.
Yeah, so I think the question about taking into account flows, obstacles, inlets, and routes. So that's certainly things that are being considered with this project with Northumbrian Water. So part of the autonomy gives the robot a sense of safety and danger. So if it's moving into a situation, so the sensing is used not just to measure artifacts, but to give the robot the ability to assess the safety or danger it's in. So if there is a sort of drop in a manhole, sort of vertical drop, then the robot should stop and then go backwards, if that makes sense, rather than keep going into a situation where it gets stuck and then needs rescue. And it feeds back obstacles and sizes. And again, if it can't go down a pipe, it will stop, report where the obstacle is, and then come back to where it can be recovered.
I was just wondering, Josh, if you're still there, you gave the first presentation talking about the CCTV. Is there anything you've heard from the other presentations that particularly you think is going to be relevant going forward, perhaps adding additional sensors onto what is a conventional CCTV survey?
Yeah, I think as I alluded to already, I think the work that Kirill and Simon are doing to add more sensors to their devices and actually robotize a lot of this work is hopefully the future for a lot of sewer inspection. I think we can get much more accurate results, and I feel like actually the algorithms that developed off the back of these sensors will hopefully help a lot of sewer inspection become more uniform and more reliable. I think it's more of a challenge in the UK, but there's very different qualities between different surveyors and different reasons for doing a lot of surveys, which means there's, as I kind of alluded to, unreliable results. So hopefully this combination of a suite of sensors and the algorithms to support them that can be implemented in a really quickly and efficiently with robots. That's what I'm hoping for the future. So keen to see where it goes, and again, equally looking for those collaboration opportunities.
Well, Josh, exactly right, because Josh, the CCTV survey and automatic recognition, AI recognition of the features can be made so much more efficient, because a lot of the pipe is just not interesting for the AI, the algorithms. It's nothing in there. So identifying where it is with acoustic data and focusing on those which are problematic, so can be made robots so much more efficient and so much more autonomous.
100%, and I guess that's the thing with we're starting to see it with getting these algorithms out on site, and so you're on battery power on a small laptop computer, but that's even more important when you're a robotic device, right? You want to use the most efficient low energy cost sensors you can, and then only when you really need to, you want to whack on your graphics card or even something much smaller to do all that processing with the AI.
That was also Manuel. Is there another question? Man,
got his hand.
Yes. Tom, are you unmute? You've raised your hand.
Yeah, I did. I was wondering with these techniques and also the combination with AI for the interpretation of these techniques, maybe it would gain a lot of use in practice. It was also combined with more information around the sewers. Like if talking about risks, then you don't need to inspect everywhere. There are certain places in a city where you rather don't like to have a collapse. So you could focus your techniques on certain areas of the whole sewer of urban drainage system. And I think the operators normally don't want to know the condition of the sewer, but they want to know when to react and which risks there are in place. So the combination with more information from outside the actual pipes would make it much more useful.
I think Colin is part of the Pipebots project, as well as the robotics and the sensing. We've also been developing planning tools based on historical failures within a network, so that you can try and plan where robots should go into pipes that have the highest likelihood of having a failure based on historical records. So our vision is, as you start to collect, you put the robots, although robots seem a great idea, our networks are huge and they don't go very fast. So you can deploy them with the most efficiency in the pipes that have the highest likelihood of failure. And that's the biggest way to make them more efficient, is to put them in the right place. So we're also developing planning tools that will allow you to plan where your robot should inspect based on your needs, and whether that's the likelihood of failure or the consequence of failure. It allows the robotic systems to have a plan and go where they gain most valuable data at a reasonable time interval.
I think just to add to that point that Simon's made as well, I think this kind of optimization of where you should be putting your sensors goes beyond everything. Even our sewer level monitors project at the moment in South West Water, where we're just simply putting monitors in manholes that are low cost, and they tell us what the depth of water is in those manholes. We've got hundreds of thousands of manholes, and there's a big problem there as to where to put them to get the best value for money. So I think that challenge is really relevant when we've got a very expensive and very, very complicated piece of kit. But I think that applies to almost every sensing technology we've talked about today, how we roll these out in a really efficient way, because they aren't all incredibly cheap at the moment. Maybe in 10 years' time, when economies of scale help out the kind of manufacturing cost of these techniques and complexity of them. But for the time being, we want to get the most bang for our buck as a water company. So that's a really interesting challenge.
I was just wondering, Manuel, are you still here?
Yes.
You gave the second presentation, the one about the sediment dynamics, as a reminder for everybody. What have you learned today, or what do you?
No, I learned that from a lot of things that inspections of urban drainage systems is still a challenging problem, and it will be like this in the upcoming years. And I would like just to continue a little bit what just mentioned right now. It's true that now perhaps the challenges in the low cost sensing and implementation in a real scale will be just to optimize like where to put it, and also combine this with perhaps prior knowledge of some failures or some parts of the sewer network. And for that, the combination with these inspections techniques that the rest of colleagues showed today is very relevant. And also, I would like to highlight how powerful are these also inspection techniques, because we saw several applications today, but I'm sure that combine this with computer vision techniques will raise a lot of more applications just using the same type of instruments, devices, and methods. But perhaps, like, I'm thinking, for example, combine with this with digital twins, so you will have like for example, with the Pipebots or similar, the CCTV vehicles, you can have like this kind of 3D reconstruction, because you have a lot of images in the sewer network. So you will have, in terms of geometry, like a digital twin of your network, and perhaps it will be very easy to identify or easier to identify spots with critical problems related with failures or related with sediment accumulation or other stuff.
And Johan, I see you've switched on your camera. What have you learned today, or what do you have any particular observations on what you've heard?
Well, I find particularly inspiring that there's quite a lot of diversity in techniques and types of research being applied to different parts of the urban drainage system, but more or less we all have a common goal, and that's obtaining more information about the structural integrity of our aging infrastructure. And that's, I mean, it's been a challenge for many decades, of course, but we really see that the approaches are more or less the spread between these is increasing, and I mean, AI is giving us a lot of new potential, but also seeing, for instance, in Sheffield, the approach being applied of using small robotics compared to, for instance, Josh's presentation on using CCTV data and obtaining more information on that. It's quite nice.
Yeah, Ton, you've got your hand up again, or was it the same hand?
Yeah. Yeah, no, it's a new hand. I was wondering if we're starting to put these techniques in practice, and we're gaining a lot of data on results of inspection and other sensors. It would be, of course, a great plus if we could collect all these practical data combined with the circumstances they are collected in, so we can learn from one situation for applying it to the other situation. So we don't need to use these sensors on all situations, but we can, make some lessons that in which situations it's more likely to occur certain failures. Is it a bit clear what I mean?
Yeah.
It comes to, I thought it was also a purpose of the Co-UDlabs to bring data together.
Yes.
So I wonder what's the progress made in that field?
Yes, we will be touching upon this, I think, when we looked at the joint research activities in the webinar on the 11th of March, which is towards the end of the project. I was wondering, though, Alma, with the U-drain, whether this U-drain community going forward might be a suitable venue for that.
Yeah, this is one of the aims of the U-drain, to try and, I guess, communicate more. And as you say about what Tom mentioned, so if on the Co-UDlabs website, some of the latest of sort of the harmonization of data, there's some latest deliverables actually posted as well on the website. Although I think the very latest is not yet there, but I can find the links. But yeah, and as Ian said, there'll be a webinar, is it the 11th of March, where there also will be some more information on the latest progress.
I was also aiming, because a lot of Co-UDlabs projects were in laboratories, but when we're moving towards implementing these kind of techniques also in practice, then we gain a lot of more data just out of practice. And combining these sensor data with the circumstances they are used in, then we could maybe got relations between certain kind of materials, pipes, or configuration of the drainage system, which will oftenly or apparently lead to a higher risk of certain failures. So we could learn together faster from the experiences than each network owner for himself.
Yes. I think it's going to be very important, the follow-up with the U-drain. The example that you've presented today, where you as Rioned used Co-UDlabs to do a pilot, and now you're doing it for practice in the field. I think we will find that quite a few of the other transnational access projects, this type of thing is probably happening. And I think Alma, Simon, the sort of feedback we've got here when we're discussing in the next few months, you know, what are we doing next after Co-UDlabs, and we will be looking at to formulate applying for further EU funds to carry forward Co-UDlabs. All this can be brought into that.
It is quite hard actually to get the funding for this, because we're trying already, even before the Co-UDlabs and the Joint Committee Urban Drainage, to in the newsletter keep gathering like information on open data sets and then sort of circulate this. But it seems getting long-term funding, so that's why we with the UDrain group we kind of hope to be that a platform for people to keep sharing, I guess, the latest information about data sharing. Because we also realized in the Netherlands there's like an urban drainage dictionary, so we've been trying to translate this. So this was one of the Co-UDlabs activities, to try to translate this also in English. That I guess ontologies are missing. Madam Jurk had to explain to me even what an ontology was here. But there's some, I'll put it in the, I've just managed to find a link. So there's especially the last 2.5 deliverable report. Sorry for the numbers for any of the audience, but this is just the internal. So you can see on the dissemination page of Co-UDlabs all sorts, and especially the report 2.5 also goes in a bit of the like data sharing and the difficulties we currently have between all the different laboratories having different definitions, different descriptions about the data. But we hope, especially in the UDrain group, to keep gathering this, to keep moving towards like a common ontology and a common description of data. I think Simon's got his hand up.
Yeah, I think, Paul, you're about right. We sort of struggle as academics in the sense that there are so many water utilities and companies and organizations that it's really difficult to get a common view on where everybody wants to go, or a large number of people want to go, and then being able to get the information out to those people or those organizations to talk to us and really describe what their needs are, if that makes sense. So that we certainly find this fragmented nature of, you know, water management difficult to deal with.
Yeah, and it's difficult to actually just link, because especially in the UK, a lot of open data sets are coming available on combined sewer overflow. And we already had a lot of open data sets on rainfall, accessible for researchers on rainfall radar and open to everyone, like census data and LiDAR data. But just combining these with their different sort of data referencing systems, it's not entirely straightforward.
Oh. It's an interesting challenge.
It is. Well, I think it's been a useful morning and a useful discussion that we've had just now. You will receive details about the next webinar where we'll be talking about the joint research activities. And I think in the meantime, for anybody who's been listening in today, do go and have a look at the Co-UDlabs website. You will find that a lot of what we've been talking about is covered on there, and there's been plenty of links which Alma has been diligently putting into the chat for us. So unless we have I have not seen any hands up or further questions.
No, and even with the small number, if people would like to say something, I invited people to, because we can unmute them.
Yes.
Especially we have a few, but there doesn't seem to be.
No. So I think
final shout out.
I think that'd be
everyone wants their lunch, maybe.
Yes, exactly. I think it probably remains for Alma, for you and I to thank the speakers for putting their time in today, and the audience. And we did reach, I think, nearly 50, which was more or less what we were expecting at one point during the during the event. So thank you for everybody who's attended. Thank you for your contributions. We look forward to taking all of this forward in the future.
Yes, thank you everyone from me also.
And to Thomas for doing a lot of the organizing of this.
Yes, and Lindsay as well.
Yes.
Thanks for inviting us.
Yeah, thank you all
So,
for interesting
bye.
morning.
Thank you.
Bye bye.
Thank you.
Thank
very
you. It
much.
was a pleasure.
Have a nice day.
So,
Simon, thanks for taking over. Speak to you later.
Okay,
Oh, I've
thank
got
you.
lots of
Bye.
thanks.
Bye. Lunchtime, I think. Well,
Yes, that prompted a lot of thanks in the chat. So yes.
yes, thank you, everyone.
Okay.
Thanks. Ciao, ciao.
Okay.
Bye bye.